Right now, as you listen to this, there is a world in our solar system that is almost identical to Earth in size, yet utterly hostile to anything we would recognize as life. This world shines brighter than any star in our night sky. Ancient civilizations called it the morning star and the evening star, never realizing they were seeing the same object. The Romans named it Venus after their goddess of love and beauty, a tragically ironic choice for what turned out to be the most hellish landscape in the inner solar system. Venus is Earth's closest planetary neighbor, and in many ways, it is Earth's twin, but something went catastrophically wrong. Stand on the surface of Venus, if you somehow could, and you would be crushed, roasted, and dissolved simultaneously. The atmospheric pressure at ground level reaches 92 times that of Earth, equivalent to being 1 kilometer beneath the ocean. The temperature holds steady at 737 Kelvin, which translates to 464 degrees Celsius or 867 degrees Fahrenheit. Lead melts at 327 degrees Celsius. Aluminum melts at 660 degrees. The surface of Venus is hot enough to melt both. Above your head, clouds of sulfuric acid stretch across the entire planet, yellow and churning, moving at hurricane speeds even though the planet itself barely rotates. Rain never reaches the ground because it evaporates in the scorching air miles above the surface. This is not just hot. This is beyond any natural heat we experience on Earth. This is what happens when a planet-sized greenhouse effect runs completely out of control. The tragedy of Venus lies in its similarity to Earth. Venus has a diameter of 12,104 kilometers compared to Earth's 12,756 kilometers. That makes Venus 95% the size of Earth. In terms of mass, Venus weighs in at 4.867 times 10 to the 24th power kilograms, while Earth masses 5.972 times 10 to the 24th power kilograms. Venus contains 81.5% of Earth's mass. The two planets share nearly identical densities, suggesting similar internal compositions. Both have iron and nickel cores surrounded by rocky mantles rich in silicates and minerals, topped with thin crusts. Both are terrestrial planets made of rock and metal rather than gas. They were born at the same time from the same cloud of material, 4.6 billion years ago, in the same region of the solar system. They are siblings in every meaningful sense. Yet their fates diverged dramatically. Earth became a blue oasis teeming with life, covered in liquid water, breathing oxygen, maintaining temperatures that hover in a comfortable range for carbon-based biology. Venus became a yellow nightmare wrapped in poison clouds, completely dry, breathing carbon dioxide so thick it behaves almost like a liquid, maintaining temperatures that would sterilize any known organism in seconds. Understanding why these two similar worlds ended up so different is one of the most important questions in planetary science. The answer affects how we think about climate change on Earth. It determines how we search for habitable planets around other stars. It shapes our understanding of what makes a world livable and what pushes a planet past the point of no return. Venus orbits the Sun at an average distance of 108 million kilometers or 67 million miles. Earth orbits at 150 million kilometers or 93 million miles. Venus receives about twice the solar energy that Earth does because of this closer proximity. That extra heat was likely the first domino in a chain reaction that transformed Venus into hell. But proximity to the Sun alone does not explain everything. Venus lacks something Earth has that proved crucial to our planet's survival. Venus has no magnetic field. Earth's magnetic field, generated by our spinning liquid iron core, shields us from the solar wind. That protective bubble prevents our atmosphere from being gradually stripped away into space. Venus lost that protection, assuming it ever had it, and the consequences cascaded through billions of years. The planet rotates retrograde, meaning it spins in the opposite direction compared to most planets in the solar system. If you could see the Sun from Venus's surface through the thick cloud cover, it would rise in the west and set in the east. Even more bizarre, Venus rotates incredibly slowly. One complete rotation takes 243 Earth days. Meanwhile, Venus completes one orbit around the Sun in only 225 Earth days. This means a day on Venus is longer than a year on Venus. A single solar day on Venus, measured from one sunrise to the next, lasts 116 Earth days and 18 hours because the planet's orbital motion works against its rotation. This strange rotation has puzzled scientists for decades, and we still do not fully understand what caused it. The leading theories involve either a massive impact that knocked Venus spinning backward, or the gravitational effects of the Sun acting on Venus's dense atmosphere over billions of years, or perhaps both. The brightness of Venus in Earth's sky stems from its position and its clouds. Venus orbits between Earth and the Sun, making it an inner planet from our perspective. As it moves through its orbit, Venus goes through phases like the Moon, displaying crescents and gibbous shapes when viewed through telescopes. When Venus passes between Earth and the Sun, we call this inferior conjunction. When Venus lies on the opposite side of the Sun from Earth, we call it superior conjunction. The greatest brightness occurs when Venus is a crescent, not when it is full, because at crescent phase, Venus is much closer to Earth despite showing less of its illuminated hemisphere. The clouds covering Venus reflect about 75% of the sunlight that hits them. Earth reflects only about 30%. This high reflectivity, called albedo, combined with Venus's proximity to Earth during certain orbital alignments, makes Venus the brightest natural object in our sky after the Sun and Moon. At its brightest, Venus reaches an apparent magnitude of -4.6, bright enough to cast shadows on Earth under dark conditions. Ancient cultures tracked Venus obsessively without understanding what they were observing. The Maya built their calendar partly around Venus's movements and associated the planet with warfare and important rituals. The Babylonians recorded detailed observations of Venus's position among the stars going back thousands of years, using this data to predict future positions. The Greeks initially thought Venus was two separate objects, calling the morning appearance Phosphoros and the evening appearance Hesperos. Pythagoras is credited with recognizing these as the same object around 500 BCE. The regular patterns of Venus's appearance and disappearance from Earth's sky made it important in astrology, mythology, and early astronomy across virtually every civilization that looked up at the night sky. Galileo's observations of Venus in 1610 provided crucial evidence for the Copernican model of the solar system. Through his telescope, Galileo saw that Venus displayed phases like the Moon, transitioning from full to crescent and back. This could only happen if Venus orbited the Sun rather than the Earth. In the old Earth-centered Ptolemaic system, Venus would always appear as a crescent because it supposedly moved around a point between Earth and Sun. Seeing Venus at gibbous and full phases proved the planet was on the far side of the Sun at those times, supporting the Sun-centered model. These observations helped shift humanity's understanding of our place in the cosmos, ironically using the planet named for love to demolish our special position at the center of creation. Modern observations revealed the true nature of the hostile world behind the brilliant appearance. The dense clouds that make Venus so reflective also hid its surface completely. For centuries, scientists could only speculate about what lay beneath. Some imagined tropical jungles dripping with moisture. The thick clouds suggested abundant water, and Venus's proximity to the Sun would provide ample heat for lush growth. Science fiction writers of the early 20th century set adventures in Venusian swamps teeming with exotic life. Reality proved far stranger and more brutal. The clouds are not water vapor, they are sulfuric acid. The atmosphere is not oxygen and nitrogen. It is 96.5% carbon dioxide and 3.5% nitrogen, with traces of sulfur dioxide and other compounds. The surface temperature and pressure make Venus more extreme than any environment on Earth, including the deepest ocean trenches or the hottest deserts. Why does Venus matter to us here on Earth? Beyond scientific curiosity, Venus serves as a laboratory for understanding planetary evolution and climate physics. Venus shows us what happens when greenhouse warming runs to completion without any mechanism to stop it. On Earth, we have a carbon cycle that regulates atmospheric carbon dioxide over geological timescales. Rain dissolves carbon dioxide from the air, forming carbonic acid. This weak acid weathers rocks on land, and rivers carry the dissolved minerals to the ocean. Marine organisms use these minerals to build shells and skeletons made of calcium carbonate. When these organisms die, their remains sink to the ocean floor, eventually getting buried and locked away in sedimentary rocks. Plate tectonics subducts these rocks back into Earth's mantle, where heat releases the carbon dioxide again through volcanic eruptions. This cycle prevents carbon dioxide from building up endlessly in our atmosphere or being removed completely. The cycle requires liquid water and active plate tectonics, and it operates over millions of years. Venus has neither. Without liquid water, weathering of rocks does not remove atmospheric carbon dioxide. Without plate tectonics, there is no mechanism to recycle materials between the surface and interior on a continuous basis. All the carbon dioxide that ever outgassed from Venus's interior through volcanic eruptions stayed in the atmosphere or got locked in surface rocks that never subducted. The result is an atmosphere so dense with greenhouse gases that it traps virtually all incoming heat. The greenhouse effect is not inherently bad. Earth's natural greenhouse effect makes our planet about 33 degrees Celsius warmer than it would be without an atmosphere, bringing us from a frozen minus 18 degrees Celsius average to a comfortable plus 15 degrees Celsius average. Venus's runaway greenhouse effect makes the planet roughly 500 degrees Celsius hotter than it would be based on its distance from the Sun alone. Understanding this process helps us understand the limits and dangers of atmospheric composition changes on Earth. Studying Venus also matters for the search for life beyond our solar system. Astronomers have discovered thousands of exoplanets orbiting other stars, many of them roughly Earth-sized and located in the habitable zone where liquid water could potentially exist. But Venus sits nearly in the habitable zone too, and it is utterly lifeless. Size and orbital distance alone do not guarantee habitability. We need to understand what makes a planet habitable and what factors push it past the edge into runaway conditions. Venus provides a nearby example of a failed habitable world, a cautionary tale written in sulfuric acid and heat. Every measurement we make of Venus's atmosphere, surface, and interior adds to our understanding of planetary physics and improves our ability to identify truly Earth-like worlds elsewhere in the galaxy. The story of Venus is a story of transformation. This planet was not always as we see it today. Evidence suggests Venus may have been more Earth-like in its distant past, possibly even possessing liquid water oceans for billions of years. Something changed. The mechanisms that allowed Earth to maintain stable conditions failed on Venus or never functioned properly in the first place. The planet crossed a threshold, and once crossed, there was no going back. The water evaporated, the carbon dioxide accumulated, the temperature soared, and Venus became locked in its current state. What we see now is the end result of billions of years of planetary evolution gone wrong. To understand how we got here, we need to go back to the beginning, to the formation of the solar system itself, and watch Venus being born. Chapter 2: Birth of the Morning Star. 4.6 billion years ago, there was no Venus. There was no Earth. There was no Sun. In the region of space where our solar system now exists, there was only a vast, cold, dark cloud of molecular hydrogen gas mixed with traces of heavier elements. This cloud, called a molecular cloud or nebula, stretched across dozens of light years and contained enough material to form thousands of stars. It drifted through the galaxy, slowly rotating, gradually accumulating more mass from the diffuse gas filling interstellar space. The cloud was cold, perhaps only 10 or 20 Kelvin above absolute zero. The gas existed in a delicate balance. Gravity pulled inward, trying to collapse the cloud. The internal gas pressure and the cloud's rotation pushed outward, resisting collapse. This balance could persist for millions of years. Something disturbed the equilibrium. The exact trigger for our solar system's formation remains uncertain, but the most likely culprit is a nearby supernova explosion, when massive stars exhaust their nuclear fuel and explode. They produce shockwaves that ripple through the surrounding interstellar medium at thousands of kilometers per second. If such a shockwave hit our molecular cloud, it would have compressed the gas, increasing its density in some regions. Once density increased enough in certain spots, gravity gained the upper hand. The cloud began to collapse. This was not a uniform collapse of the entire cloud at once. Instead, the cloud fragmented into many smaller clumps, each collapsing independently. Each clump would eventually form its own star system. One of these clumps, no more exceptional than countless others, would become our Sun and its family of planets. As the clump collapsed under its own gravity, it began to spin faster. This is conservation of angular momentum, the same principle that makes ice skaters spin faster when they pull their arms in. The collapsing cloud was not perfectly uniform. Random variations in density and motion meant different parts collapsed at different rates and with different amounts of rotation. The material naturally settled into a disk shape because rotation was fastest in the plane perpendicular to the spin axis. Imagine the cloud as a slowly rotating sphere at first. As it collapses, material falling toward the center along the spin axis encounters less resistance than material falling in from the sides. The material from the sides ends up with more angular momentum and gets flung outward into a disk. Within roughly 100,000 years of the initial collapse, the system transitioned from a diffuse cloud to a central concentration of mass surrounded by a flattened rotating disk. The center of this disk, where most of the mass concentrated, became increasingly hot as gravitational potential energy converted to thermal energy. Particles falling inward picked up speed, and when they crashed into the growing central mass, their kinetic energy turned into heat. The temperature climbed to thousands of Kelvin. The pressure soared as more and more material accumulated. After approximately 10 million to 50 million years, the temperature and pressure at the core of this protostar reached the threshold for nuclear fusion. Hydrogen atoms began fusing into helium, releasing tremendous energy. The sun ignited. At this moment, our star transitioned from a collapsing ball of gas heated by gravity alone to a stable star powered by nuclear reactions. The outward pressure from fusion radiation balanced the inward pull of gravity, and the sun stabilized at roughly its current size and brightness, though it would gradually brighten over billions of years as its composition changed. The disk surrounding the young sun, called a protoplanetary disk, contained all the raw material that would eventually form the planets, moons, asteroids, and comets. The disk was massive, perhaps containing several percent of the sun's mass, though most of this material would eventually fall into the sun or be ejected from the system. The temperature in the disk varied dramatically with distance from the sun. Close to the star, temperatures reached thousands of Kelvin, hot enough to vaporize almost everything. Only the most refractory materials, substances that require extremely high temperatures to vaporize, could exist as solids in the innermost regions. These included metals and silicate minerals. Farther out, beyond a certain distance called the frost line, temperatures dropped below the freezing point of water. Beyond this line, water ice could exist as a solid, along with frozen carbon dioxide, methane, and ammonia. This temperature gradient would fundamentally shape the types of planets that formed at different distances. The material in the disk was initially gas and tiny dust grains, with dust making up only about 1% of the mass. The gas was primarily hydrogen and helium left over from the Big Bang. The dust consisted of microscopic particles of rock, metal, and ice, depending on location. These grains collided with each other constantly as they orbited the sun within the disk. Sometimes collisions destroyed grains, shattering them into smaller pieces. But more often, especially at slower collision speeds, grains stuck together. Electrostatic forces, the same static electricity that makes dust cling to surfaces on Earth, helped grains adhere when they touched. Gradually, over thousands of years, the dust grains accumulated into larger clumps. Millimeter-sized pebbles formed, then centimeter-sized rocks, then meter-sized boulders. This process is called coagulation or accretion. As objects grew larger, gravity became increasingly important. Objects bigger than roughly 1 kilometer across had enough self-gravity to attract nearby material actively. These kilometer-sized bodies are called planetesimals, and they represent the first true building blocks of planets. The transition from meter-sized rocks to kilometer-sized planetesimals is one of the least understood steps in planet formation. Collisions at this size scale often result in destructive fragmentation rather than growth. Several mechanisms have been proposed to bridge this gap. One possibility is gravitational instability, where concentrations of dust and pebbles become so dense that they collapse directly into planetesimals under their own gravity, skipping the intermediate destructive collision phase. Another mechanism is called streaming instability, where interactions between gas and solid particles create dense clumps that rapidly collapse. The details remain uncertain, but the result is clear from observations of other young star systems and from the existence of asteroids in our own system. Planetesimals formed throughout the protoplanetary disk within the first few million years. Once planetesimals existed, their growth accelerated. Larger planetesimals had stronger gravity and swept up smaller bodies more efficiently. This led to runaway growth, where the largest planetesimals in a region grew much faster than their neighbors, eventually dominating their orbital zones. These dominant bodies, now tens to hundreds of kilometers across, are called planetary embryos or protoplanets. In the inner solar system, where Venus and Earth would form, the temperature was too high for ice to exist. The only solid materials available were silicate rock and metal. This limited the total amount of solid material available for planet building. In the outer solar system, beyond the frost line, ice added significantly to the solid mass available, allowing planetary embryos to grow much larger and faster. The inner solar system, filled with dozens of planetary embryos, each roughly the size of Mars or smaller, competing for the remaining material in overlapping orbital zones. Collisions between these embryos were inevitable. Gravitational interactions stirred up the orbits, increasing eccentricities and inclinations until embryos that once stayed safely apart began crossing paths. When planetary embryos collide at orbital speeds, the impacts are catastrophic. Temperatures at the collision site can exceed 10,000 Kelvin. Rock vaporizes. Entire bodies can be shattered or merged, depending on the angle and speed of impact. These collisions are called giant impacts, and they dominated the final stage of terrestrial planet formation. Venus formed through a series of these giant impacts. One embryo, perhaps starting with a mass similar to Mars, occupied the orbital region roughly 108 million kilometers from the Sun. Over millions of years, this embryo collided with and absorbed other embryos. Each collision added mass and energy. The energy released by these impacts was so enormous that it melted the growing planet completely, creating a global magma ocean. A magma ocean is exactly what it sounds like, an ocean of molten rock covering the entire surface and extending potentially hundreds or even thousands of kilometers deep into the planet. The temperatures in a magma ocean range from 1500 to 3000 Kelvin or more, hot enough to keep silicate rock in a liquid state. The magma ocean phase was critical for planetary differentiation. Differentiation is the process by which a planet separates into layers based on density. In the molten state, heavy elements like iron and nickel sank toward the center, forming the core. Lighter silicate minerals floated toward the surface, eventually forming the mantle and crust once the magma ocean cooled and solidified. This process happened rapidly on geological timescales, perhaps within a few tens of millions of years, because convection in the magma ocean efficiently transporting heat and material. The sinking of iron to form the core released additional gravitational potential energy, which further heated the planet, helping to maintain the molten state. Eventually, as the rate of giant impacts decreased and the energy input dropped below the rate at which heat could be radiated away to space, the magma ocean began to solidify from the bottom up. During the magma ocean stage, any volatiles present in the infalling material, substances like water, carbon dioxide, nitrogen, and noble gases, would have been released into an overlying atmosphere. The violent impacts vaporized rocks, and the gases produced by this vaporization created a thick steam atmosphere composed mainly of water vapor, carbon dioxide, and other volatiles. This atmosphere could have been hundreds or even thousands of times denser than Earth's current atmosphere. It was hot, dense, and opaque to infrared radiation, trapping heat and maintaining the magma ocean for potentially millions of years. As long as the atmosphere remained thick and hot, it acted like a thermal blanket, preventing the magma ocean from cooling. Only when the rate of impacts slowed enough that the atmosphere could begin to radiate heat to space faster than new heat was added, could the magma oceans start to freeze. The composition of Venus's magma ocean depended on what materials accreted during its formation. Spectroscopic observations and theoretical models suggest that Venus and Earth formed from similar starting material in the protoplanetary disk. Both likely accreted a mixture of silicate rock, metallic iron, and a small fraction of volatile-rich material, possibly delivered by planetesimals that formed farther out in the solar system and were scattered inward. The exact ratio of rock to metal to volatiles would determine the planet's final bulk composition, core size, and initial volatile inventory. Recent isotopic studies comparing Venus's atmosphere to Earth's atmosphere and to meteorites have provided clues about these ratios, though many questions remain unanswered because we have never returned a sample from Venus for detailed laboratory analysis. The final stages of Venus's formation likely involved one or more giant impacts with embryos roughly the size of Mars. Earth experienced a giant impact that formed the Moon, an event so energetic it vaporized a significant portion of both the proto-Earth and the impactor, ejecting material into orbit that later coalesced into the Moon. Venus has no moon, which suggests either that Venus's giant impacts happened differently, not producing a stable orbiting disk of debris, or that any moon that did form was later lost to tidal interactions or collisions. The absence of a large moon has consequences for Venus's evolution. Earth's moon stabilizes our planet's axial tilt, preventing extreme variations that would drastically alter climate. The moon also causes tides in Earth's oceans and solid body, which dissipate energy and affect rotation. Venus, lacking a moon, evolved without these stabilizing and energy-dissipating influences. By roughly 100 million years after the initial collapse of the solar nebula, Venus existed as a recognizable planet with a differentiated interior consisting of an iron core, a silicate mantle, and a solidifying crust. The planet had a mass of 4.867 times 10 to the 24th power kilograms and a radius of 6,052 kilometers. It orbited the Sun at 108 million kilometers with a period of 225 days. At this stage, Venus may have looked quite different from its current appearance. The surface temperature was still elevated from formation energy, but much cooler than during the magma ocean phase. The atmospheric composition depended on how much volatiles were delivered during accretion and retained during the violent early impacts. This is where the story becomes controversial and uncertain. Did Venus ever have liquid water oceans? Was there a time, perhaps lasting billions of years, when Venus resembled Earth with seas, continents, and a moderate climate? Or did Venus transition almost immediately from magma ocean to runaway greenhouse, never achieving the stable conditions that allowed Earth to develop and maintain life? The answer to this question determines whether Venus is a world that fell from grace or a world that was doomed from birth. The evidence comes from measurements of atmospheric isotopes, theoretical climate models, and our understanding of planetary evolution. What comes next reveals what scientists think happened to Venus in its youth, and why the planet you see today bears no resemblance to the world that might have existed 4 billion years ago. Chapter 3: The Lost Ocean, Venus's Ancient Past. The question haunts planetary scientists like a ghost from 4 billion years ago. Did Venus ever have oceans? Was there a time when liquid water covered significant portions of the planet's surface, filling basins between volcanic highlands, creating shores and tides, perhaps even providing the conditions necessary for life to emerge? Or was Venus doomed from the moment it finished forming, too close to the Sun, too hot to ever condense water vapor into liquid, destined to become the hellscape we observe today? The answer matters profoundly because it determines whether Venus represents a cautionary tale of a planet that lost its way or simply a world that never had a chance. The evidence is circumstantial, debated, and frustratingly incomplete. But clues exist, written in the composition of Venus's atmosphere and frozen in the geological features that radar has revealed beneath the clouds. The most compelling evidence for ancient water on Venus comes from isotope ratios. Isotopes are versions of the same element with different numbers of neutrons in their nuclei. Hydrogen, the simplest element, exists primarily as regular hydrogen with one proton and no neutrons, but a small fraction of hydrogen atoms contain one neutron in addition to the proton. This isotope is called deuterium. On Earth, the ratio of deuterium to regular hydrogen in water is about 156 deuterium atoms for every million hydrogen atoms. This ratio, abbreviated as D to H, varies slightly between different reservoirs on Earth, but the bulk value is well established. When spacecraft measured the D to H ratio in Venus's atmosphere in the 1980s, they discovered something shocking. Venus has 120 to 150 times more deuterium relative to hydrogen than Earth does. This enormous enrichment demands an explanation. The leading interpretation is that Venus once had far more hydrogen than it does today, and that hydrogen was preferentially lost to space over billions of years. When water molecules in the upper atmosphere are broken apart by ultraviolet light from the sun, they split into hydrogen and oxygen. The hydrogen, being extremely light, can escape from the planet's gravitational field relatively easily, especially if the planet lacks a strong magnetic field to trap it. Regular hydrogen, with an atomic mass of 1, escapes more readily than deuterium, with an atomic mass of 2. Over time, this preferential loss of regular hydrogen leaves the remaining atmospheric hydrogen enriched in deuterium. The current D to H ratio on Venus suggests that the planet has lost an enormous quantity of hydrogen. Estimates vary, but if you calculate backward from the present enrichment, assuming Venus started with an Earth-like D to H ratio, you arrive at an initial water inventory equivalent to an ocean covering the entire planet to a depth anywhere from 3 meters to perhaps 30 meters or more. That is not a deep ocean by Earth standards, where the average depth exceeds 3 kilometers, but it is still a substantial amount of water. This interpretation, however, comes with caveats. The calculation assumes that Venus's initial D to H ratio matched Earth's, which is reasonable but not certain. It assumes that deuterium and hydrogen were lost at rates consistent with models of atmospheric escape, which depends on many factors including solar activity, atmospheric composition, and escape mechanisms that are difficult to constrain over billions of years. Some scientists argue that the high D to H ratio could instead indicate a steady state where water is continuously supplied to Venus through volcanic outgassing or comet impacts and continuously lost through hydrogen escape, with the current ratio representing an equilibrium rather than a fossil of a vanished ocean. Recent research in 2024, published in Nature Astronomy, suggested that Venus may have been born hot and never possessed surface water at all. The study analyzed the chemical evolution of Venus's interior and atmosphere using models constrained by observations of volcanic gases. The researchers concluded that the interior of Venus is dry, containing little water, and that volcanic outgassing could not have provided enough water to create oceans. If Venus never had abundant water locked in its interior, it never could have outgassed enough water to form seas, regardless of surface temperature. This newer interpretation challenges decades of thinking, but has not settled the debate. Other lines of evidence point toward at least the possibility of ancient water. In 2023, a team led by researchers from Brown University published a study suggesting that Venus had plate tectonics between 4.5 billion and 3.5 billion years ago, operating simultaneously with Earth's early plate tectonics. The evidence comes from atmospheric chemistry. Venus's atmosphere contains specific abundances of nitrogen and carbon dioxide that are difficult to explain without invoking a process to recycle materials between the surface and interior. On Earth, plate tectonics drives this recycling. Oceanic crust forms at mid-ocean ridges, spreads across the sea floor, then subducts back into the mantle at convergent boundaries. This process carries water and other volatiles into the deep Earth and brings them back out through volcanic eruptions. It also regulates atmospheric carbon dioxide over geological timescales through the carbonate-silicate cycle. Without plate tectonics and liquid water, Venus has no comparable mechanism. The study used computer models to simulate the early evolution of Venus's atmosphere. The models tested different scenarios for volcanic outgassing, atmospheric escape, and surface-atmosphere interactions. The only scenario that successfully reproduced the current abundances of nitrogen and carbon dioxide in Venus's atmosphere was one involving early plate tectonics. This suggests that Venus did have tectonic activity in its first billion years before something caused it to shut down. On Earth, plate tectonics requires water to lubricate the descent of subducting slabs and to weaken the rocks enough for them to bend and sink into the mantle. A completely dry Venus likely could not have operated plate tectonics. Therefore, if Venus had plate tectonics, it probably had at least some surface or crustal water to facilitate that process. This does not necessarily mean Venus had oceans, but it suggests the planet was not born as the desiccated world we see today. The timing of these events matters enormously. If Venus had water and plate tectonics in its first billion years, from 4.5 to 3.5 billion years ago, then the planet potentially had habitable conditions during the same period when life was emerging on Earth. Earth's oldest confirmed fossils date to about 3.5 billion years ago, though some disputed evidence suggests life may have existed as early as 4.1 billion years ago. If Venus and Earth both had liquid water, moderate temperatures, and active geological processes during this window, both planets could have been habitable simultaneously. Life might have originated on Venus. This possibility, while speculative, cannot be ruled out based on current evidence. If life did emerge on Venus, it would have perished when conditions deteriorated, but the implications for astrobiology would be profound. It would suggest that life arises readily when conditions are right, and that our solar system may have hosted two inhabited worlds in its youth. What caused Venus to lose its water, assuming it had any? The runaway greenhouse effect is the standard answer, but understanding how and when this process occurred requires examining the mechanisms in detail. Venus receives about twice the solar energy per unit area as Earth because it orbits closer to the Sun. This extra energy alone does not automatically cause a runaway greenhouse. Early in the solar system's history, the Sun was dimmer than it is today, radiating only about 70% of its current luminosity 4 billion years ago. This faint young sun paradox affects all the planets. With a dimmer sun, early Venus may have been cool enough for liquid water to exist on its surface despite its closer orbit. As the sun gradually brightened over hundreds of millions of years, Venus's climate would have warmed. A planet in radiative equilibrium balances incoming solar energy with outgoing infrared radiation. If the planet has an atmosphere with greenhouse gases, those gases trap some of the outgoing infrared, causing the surface to warm until the increased temperature radiates enough energy to balance the incoming solar flux. Earth maintains this balance with a moderate greenhouse effect contributed primarily by water vapor and carbon dioxide. As Venus warmed due to increasing solar luminosity, more water evaporated from any oceans that existed. Water vapor is a powerful greenhouse gas. More water vapor in the atmosphere means more infrared trapping, which means higher temperatures, which causes even more evaporation. This is a positive feedback loop. The process can accelerate if conditions are right. The runaway greenhouse effect occurs when the feedback becomes unstoppable. As water vapor increases, the atmosphere's infrared opacity increases until outgoing radiation plateaus at a maximum value determined by the wavelengths where water vapor does not absorb. If incoming solar energy exceeds this maximum possible outgoing radiation, the planet cannot achieve radiative balance. Temperatures rise without limit until all surface water has evaporated and the atmosphere is loaded with steam. On Earth, this runaway is prevented by a combination of factors. Earth's distance from the Sun limits incoming energy. Our planet's carbonate silicate cycle removes carbon dioxide from the atmosphere on timescales of hundreds of thousands to millions of years, preventing long-term buildup. Clouds formed from water vapor reflect sunlight, increasing the planet's albedo and partially counteracting the warming. These feedbacks maintain Earth in a stable state. Venus lacked the mechanisms to stop the runaway. Once the process began, perhaps 3.5 to 4 billion years ago, temperatures climbed rapidly on geological timescales. Within a few hundred million years, the oceans completely evaporated if they existed. The atmosphere became a thick steam bath with temperatures exceeding 600 Kelvin. At these temperatures, water molecules in the upper atmosphere were efficiently broken apart by solar ultraviolet radiation. The process is called photodissociation. Ultraviolet photons carry enough energy to sever the chemical bonds holding water molecules together. The resulting hydrogen and oxygen atoms behave very differently. Hydrogen, being extremely light with an atomic mass of 1, can reach escape velocity through thermal motion alone if it gets high enough in the atmosphere where collisions are rare. This process is called Jeans escape, or at high rates, hydrodynamic escape. Oxygen, with an atomic mass of 16, is far too heavy to escape thermally. It remained in the atmosphere or reacted with surface rocks, forming oxides. Over hundreds of millions to billions of years, Venus lost essentially all its hydrogen to space. The deuterium, being twice as heavy, escaped more slowly, leading to the observed enrichment. The oxygen either bonded with rocks on the surface, oxidizing iron and other elements, or remained in the atmosphere where it eventually combined with carbon from volcanic outgassing to form carbon dioxide. The net result was the complete desiccation of the planet. By 3 billion years ago, Venus was likely already dry and hot, with a carbon dioxide-dominated atmosphere and surface temperatures climbing toward their current extreme values. The water that might have filled seas and carved river valleys was gone, split apart atom by atom, and dispersed into the solar wind. Nothing remained except the isotopic signature preserved in the atmosphere's residual hydrogen, a ghost of what may have been. The loss of water had cascading effects on Venus's geology and evolution. Water plays a crucial role in plate tectonics on Earth. It lowers the melting point of rocks, making them softer and more pliable. It reduces friction along faults and subduction zones, allowing plates to slide past each other. It also affects the buoyancy and density of crustal materials. Without water, Venus's lithosphere became stiff and strong, resistant to the forces that drive plate motion. Mantle convection continued because the interior remained hot from radioactive decay and residual heat from formation. But the rigid lithosphere acted as a stagnant lid, preventing the convecting mantle from breaking the surface into moving plates. Heat from the interior could only escape through conduction and occasional volcanic eruptions rather than through the efficient plate recycling process that operates on Earth. This stagnant lid regime has profound implications. Without subduction to recycle crustal materials, the surface cannot renew itself continuously. Instead, Venus appears to have undergone episodic resurfacing events where volcanic activity intensified globally, covering much of the planet with fresh lava over a geologically short period. The most recent such event occurred between 300 million and 600 million years ago based on crater counts and geological mapping. Before that event, the surface may have been much older, possibly preserving features from the ancient, potentially water-bearing era. But the resurfacing erased that record, leaving a relatively young surface that tells us nothing about conditions billions of years earlier. It is as if Venus destroyed its own past, burying any evidence of ancient oceans beneath kilometers of basaltic lava. Some features visible on Venus's surface today hint at a more complex history. Tesserae are regions of highly deformed terrain, showing intense folding and faulting unlike the volcanic plains that dominate the planet. Tesserae cover only about 8% of Venus's surface, but are among the oldest visible features. They appear to have been subjected to tectonic stresses that deformed them into their current state. Some researchers suggest tesserae could represent ancient continental-like crust that formed when water was present, possibly through mechanisms similar to those that create granite on Earth. Granite typically forms in the presence of water and is associated with continental crust. If tesserae are indeed felsic, more silica-rich than typical basalt, they would require conditions quite different from those on Venus today. This interpretation is controversial because spectroscopic measurements of tesserae from orbit are difficult and ambiguous. Future missions equipped to analyze surface composition in detail may resolve the question. The story of Venus's ancient past remains incomplete. We have tantalizing hints, the deuterium enrichment suggesting massive hydrogen loss, the atmospheric composition requiring early plate tectonics, the tesserae hinting at continental-like crust, the geological evidence for episodic resurfacing that erased older terrain. We have sophisticated models showing how Venus could have maintained liquid water for billions of years under certain conditions, or alternatively, could have lost any initial water within its first few 100 million years. We have recent research arguing Venus was born hot and dry, never experiencing the temperate phase that made Earth habitable. Reconciling these contradictory lines of evidence requires more data. We need samples from Venus's surface to measure isotopic ratios in rocks. We need detailed mineralogical maps to identify ancient crust. We need better constraints on the history of solar luminosity and Venus's orbital evolution. Until we obtain that data, the question of Venus's ancient oceans will remain one of the most important unsolved mysteries in planetary science. If Venus did have oceans and lost them, the process illustrates how delicate planetary habitability can be. A planet can start with all the right ingredients and still fail if conditions shift beyond critical thresholds. The loss of water triggered changes in geology that prevented recovery. Without plate tectonics to regulate the atmosphere, carbon dioxide accumulated from volcanic outgassing with nothing to remove it. The greenhouse effect intensified, temperatures rose further, and Venus spiraled into its current state. Once begun, the transformation was irreversible. Venus serves as an example of how a planet can cross a point of no return, entering a state from which no natural process can rescue it. Understanding that transition is crucial for understanding planetary habitability throughout the universe, and for recognizing the factors that allowed Earth to remain habitable for 4 billion years while our twin planet died. Chapter 4: The Runaway Greenhouse Catastrophe. The transformation of Venus from a potentially habitable world to an uninhabitable hellscape was not instantaneous. It was a process that unfolded over hundreds of millions of years, driven by feedback loops that amplified small changes into catastrophic ones. The runaway greenhouse effect is not simply a large greenhouse effect. It is an evolutionary process, a one-way journey from equilibrium to a new, far more extreme equilibrium, with no possibility of return. Understanding this process in detail reveals why Venus became so hostile and why Earth did not follow the same path despite being similar in so many ways. The mechanisms are rooted in atmospheric physics, planetary energy balance, and the chemistry of greenhouse gases. Once triggered, the runaway greenhouse transforms everything. Begin with a planet that has liquid water on its surface and an atmosphere containing some greenhouse gases. Venus 4 billion years ago might have fit this description. The planet receives solar radiation that warms the surface. The warm surface radiates energy back towards space as infrared radiation. Greenhouse gases in the atmosphere absorb some of this infrared radiation and re-emit it in all directions, including back toward the surface. This trapped energy warms the surface further, creating a greenhouse effect. The magnitude of the effect depends on the concentration and properties of the greenhouse gases. On Earth today, the greenhouse effect raises the average surface temperature by about 33 degrees Celsius, from -18 degrees that we would have without an atmosphere to +15 degrees that we actually observe. This is a beneficial, stable greenhouse effect. Venus today has a greenhouse warming of approximately 500 degrees Celsius, raising the surface temperature from around 230 degrees Celsius, which would be the equilibrium temperature based on solar input and albedo alone, to 737 degrees Celsius. This is a runaway greenhouse effect. The transition begins when something increases the planet's surface temperature. For Venus, the most likely trigger was increasing solar luminosity as the sun aged and brightened. 4 billion years ago, the sun was about 70 to 75% as luminous as it is today. This faint young sun meant Venus received less energy despite its closer orbit. As the sun brightened over hundreds of millions of years, Venus received more energy and surface temperatures gradually increased. Warmer surface temperatures cause more evaporation from oceans. Water vapor enters the atmosphere in larger quantities. Water vapor is a potent greenhouse gas, absorbing infrared radiation strongly across multiple wavelength bands. The increased water vapor traps more outgoing infrared radiation, warming the surface further. This is positive feedback. More heat causes more evaporation, which causes more warming, which causes more evaporation. On Earth, this feedback is limited by several factors. As water vapor increases, the atmosphere becomes more humid. Eventually, the air cannot hold more water vapor without condensing it into clouds or precipitation. Clouds have complex effects on climate. They reflect incoming solar radiation, cooling the planet. They also trap outgoing infrared radiation, warming the planet. The net effect depends on cloud altitude, thickness, and composition. On Earth, clouds provide a negative feedback that helps stabilize climate. Additionally, Earth's oceans are vast. But the rate of evaporation is limited by the rate at which solar energy can supply the necessary latent heat of vaporization. Earth's carbonate silicate cycle also removes carbon dioxide from the atmosphere, preventing excessive greenhouse warming from carbon dioxide buildup. Venus lacked these stabilizing mechanisms, or they were insufficient to prevent runaway. As temperatures rose, evaporation accelerated. The atmospheric water vapor content increased dramatically. Venus's smaller distance from the Sun meant more solar energy was available to drive evaporation. The increased water vapor enhanced the greenhouse effect, raising temperatures further. At some point, the feedback became unstoppable. The atmosphere's ability to radiate energy to space plateaued because water vapor absorbed infrared radiation so efficiently across such broad wavelength ranges that very little radiation could escape. There is a theoretical maximum outgoing radiation limit for a water vapor-dominated atmosphere, typically around 280 to 310 watts per square meter. Once incoming solar radiation exceeded this limit, the planet could not radiate away all the energy it received. The only way to achieve energy balance was to keep warming the surface until emission at wavelengths where water vapor does not absorb could carry away the excess heat. But as the surface warmed, more water evaporated, increasing water vapor, which absorbed more radiation, requiring even higher temperatures. The loop was unstoppable. Temperatures soared. Estimates suggest that during the runaway phase, surface temperatures may have climbed to 800 or 900 Kelvin or even higher. The oceans boiled entirely into the atmosphere. Venus was enveloped in a thick steam atmosphere with surface pressures potentially reaching hundreds of bars. The atmosphere became opaque to radiation across most wavelengths. Heat could not escape efficiently. The planet resembled a pressure cooker on a cosmic scale, trapping energy with no release valve. This phase may have lasted tens to hundreds of millions of years. During this time, any life that might have existed on Venus would have been exterminated. Any geological processes that required liquid water would have ceased. The surface became a hostile environment where no complex chemistry could persist. Water molecules reaching the upper atmosphere were exposed to intense solar ultraviolet radiation. Ultraviolet photons with wavelengths shorter than about 240 nanometers carry enough energy to break the bonds in water molecules through photodissociation. The reaction splits water into hydrogen and oxygen. In the upper atmosphere, where the gas density is low, these atoms can travel significant distances before colliding with other particles. Hydrogen, with its low mass, moves at high average speeds even at moderate temperatures. If hydrogen atoms in the upper atmosphere have enough velocity to exceed the planet's escape velocity, they leave Venus permanently. This process is called hydrodynamic escape, when the rate is high enough that the escaping hydrogen drags other atmospheric gases along with it. Escape velocity from Venus's surface is about 10.4 kilometers per second. In the upper atmosphere, several hundred kilometers above the surface, where gravitational pull is weaker, the required velocity is lower. Hydrogen atoms at these altitudes, heated by solar ultraviolet absorption and by exothermic chemical reactions, can reach the necessary speeds. During the runaway greenhouse phase, the escape rate would have been enormous, potentially exceeding 10 to the 14 power hydrogen atoms per square centimeter per second. At this rate, Venus could lose the equivalent of an Earth ocean of water in a few hundred million years. The oxygen atoms left behind were far too heavy to escape. Oxygen has 16 times the mass of hydrogen, and its thermal velocity at the same temperature is 4 times slower. Oxygen remained in the atmosphere or reacted chemically with surface rocks. The oxidation of surface rocks consumed much of the oxygen. Iron in basaltic rocks, for example, can react with oxygen to form iron oxides, essentially rusting the surface. Sulfur compounds released by volcanic activity also reacted with oxygen. Over time, the atmospheric oxygen was scrubbed out, locked into minerals on the surface. Some oxygen may have been incorporated into carbon dioxide as volcanic carbon outgassed and combined with available oxygen. The net result was the removal of essentially all hydrogen from the planet, while the oxygen was sequestered in the crust or combined into other molecules. By the time the runaway greenhouse phase ended, Venus had lost the equivalent of any initial water inventory it may have possessed. The runaway greenhouse eventually stabilized when all surface water had evaporated and been lost. Without additional water to provide water vapor, the steam atmosphere could no longer maintain itself. Water vapor at high altitudes continued to be photodissociated and lost, gradually drying the atmosphere. As water vapor declined, its greenhouse contribution decreased, but by this time, other processes had taken over to maintain high temperatures. Volcanic activity continued releasing carbon dioxide from Venus's interior. On Earth, carbon dioxide released by volcanoes is removed from the atmosphere through weathering and carbonate formation in the presence of liquid water. Without water, Venus had no mechanism to remove atmospheric carbon dioxide. Every molecule outgassed by volcanoes stayed in the atmosphere. Over hundreds of millions to billions of years, carbon dioxide accumulated to enormous concentrations. Carbon dioxide is a less potent greenhouse gas per molecule than water vapor, but at high concentrations and high pressures, it becomes extremely effective at trapping heat. Venus's current atmosphere is 96.5% carbon dioxide with a surface pressure of 92.1 bar. This is 92 times Earth's atmospheric pressure and contains roughly 500,000 times as much carbon dioxide as Earth's atmosphere. The sheer quantity of carbon dioxide creates a greenhouse effect that maintains surface temperatures at 737 Kelvin. The atmosphere is so dense that at the surface, the carbon dioxide exists as a supercritical fluid, a state of matter that has properties of both a gas and a liquid. Supercritical carbon dioxide flows like a fluid but fills space like a gas. This extreme state is only possible because of the combination of high temperature and high pressure. The transition from a water, vapor-dominated runaway greenhouse to a carbon dioxide-dominated stable greenhouse marked the final transformation of Venus. By 3 to 3.5 billion years ago, Venus likely resembled its current state in terms of atmospheric composition and surface temperature, though details such as volcanic activity levels and cloud structure may have differed. The planet had reached a new equilibrium, vastly different from its starting conditions. This new state is stable on timescales of billions of years. As long as the Sun continues shining at roughly its current luminosity and Venus maintains its carbon dioxide atmosphere, the conditions will persist. Nothing in Venus's natural environment can reverse the process. There is no mechanism to remove the carbon dioxide. There is no way to cool the surface enough for water to condense, even if water was somehow delivered. Venus is locked into its current state. The runaway greenhouse effect on Venus serves as a warning for understanding climate on other planets and on Earth. It demonstrates that planetary climates are not inherently stable. They can undergo irreversible transitions if feedback loops are triggered. The critical factor is whether negative feedbacks exist to counteract positive feedbacks. Earth has several negative feedbacks that have maintained climate stability for billions of years. The carbonate-silicate cycle regulates carbon dioxide on timescales of hundreds of thousands to millions of years. Increased carbon dioxide causes warming, which accelerates weathering, which removes carbon dioxide from the atmosphere, reducing greenhouse warming. This negative feedback stabilizes Earth's climate against perturbations. Clouds and ice cover provide additional feedbacks that, while complex, generally help maintain stability. Venus lacked these stabilizing feedbacks, or they were overwhelmed by positive feedbacks. The planet's proximity to the Sun provided enough energy to push it past a critical threshold where feedbacks amplified changes rather than damping them. Once past that threshold, there was no recovery. The concept of a habitable zone around stars is based partly on avoiding conditions that lead to runaway greenhouse effects. Planets too close to their stars receive too much energy and risk transitioning to Venus-like states. Planets too far from their stars are too cold for liquid water to exist on their surfaces, at least with Earth-like atmospheres. The habitable zone represents the range of distances where liquid water can persist given reasonable assumptions about atmospheric composition and planetary properties. Venus orbits at 108 million kilometers from the Sun, Earth at 150 million kilometers. This 42 million kilometer difference, combined with other factors such as lack of a magnetic field and possibly different initial volatile inventories, determine the planet's divergent fates. Understanding the precise conditions that trigger a runaway greenhouse effect informs the search for habitable exoplanets. Astronomers discovering Earth-sized planets in the habitable zones of distant stars must consider not just orbital distance, but also atmospheric composition, stellar activity, planetary rotation rate, magnetic field presence, and many other factors that influence climate stability. Venus teaches us that size and location are not enough to guarantee habitability. The devil is in the details of atmospheric physics and planetary evolution. The runaway greenhouse catastrophe on Venus was the pivotal event in the planet's history. It transformed Venus from whatever it had been, potentially an Earth-like world with water and moderate temperatures, into the hostile environment we observe today. The process was irreversible, driven by fundamental physics and chemistry. Once triggered, the feedbacks guaranteed that Venus would reach its current extreme state. No intervention short of massive planetary engineering could reverse it. The sulfuric acid clouds that now enshroud Venus, the crushing atmospheric pressure, the lead-melting temperatures, the complete absence of water are all consequences of this ancient catastrophe. To understand Venus today, we must understand this process. To understand what makes Earth habitable, we must understand why Earth avoided Venus's fate. The atmosphere of Venus is not just thick and hot. It is the result of billions of years of evolution following a climate disaster that remade the planet entirely. Chapter 5: Anatomy of Hell, the Venusian Atmosphere. The atmosphere of Venus is not merely thick. It is not simply hot. It is a crushing, corrosive, multi-layered inferno that would destroy any spacecraft within hours and any unprotected human within seconds. Standing at the surface, if you could somehow survive, you would experience conditions more extreme than anything naturally occurring on Earth. The weight of the atmosphere pressing down on you would equal the pressure you would feel 1 kilometer beneath Earth's oceans. The temperature would melt lead, zinc, and tin. Above your head, clouds of concentrated sulfuric acid would stretch across the entire sky, forever hiding the sun and stars. The atmosphere itself would be so dense that it would not feel like air. It would resist your movements like water, flowing around you with strange, viscous behavior. This is Venus's atmosphere, the deadliest in the inner solar system, and understanding its structure reveals how far a planet's atmosphere can diverge from Earth-like conditions. The surface pressure on Venus reaches 92.1 bar. 1 bar is approximately the atmospheric pressure at sea level on Earth. 92 bars means that every square centimeter of surface bears the weight of 920 kilograms of atmosphere above it. This immense pressure results from the sheer quantity of gas in Venus's atmosphere. The total mass of Venus's atmosphere is approximately 93 times greater than Earth's entire atmosphere. Most of this mass consists of carbon dioxide. The atmosphere is 96.5% carbon dioxide by volume, with nitrogen making up most of the remaining 3.5%. Trace amounts of sulfur dioxide, water vapor, carbon monoxide, argon, and other gases account for less than 1%. The dominance of carbon dioxide fundamentally shapes the atmosphere's properties. Carbon dioxide at 92 bars and 737 Kelvin exists in a state that straddles the boundary between gas and liquid. The critical point of carbon dioxide, above which the distinction between gas and liquid phases disappears, occurs at about 74 bars and 304 Kelvin. Venus's surface conditions exceed the critical pressure and far exceed the critical temperature. Carbon dioxide at the surface behaves as a supercritical fluid, possessing properties of both phases. It has the density approaching that of a liquid, about 65 kilograms per cubic meter, compared to Earth's sea level air density of about 1.2 kilograms per cubic meter. Yet it flows and expands to fill available space like a gas. This supercritical state means that carbon dioxide at Venus's surface can dissolve substances and transport heat more efficiently than ordinary gas. It also means the atmosphere near the surface is incredibly viscous and sluggish. Temperature at the surface averages 737 Kelvin, which translates to 464 degrees Celsius or 867 degrees Fahrenheit. This temperature is remarkably uniform across the planet. Measurements from multiple landing sites spread across different latitudes and longitudes all recorded temperatures within a few degrees of this average. Day and night make virtually no difference. The equator and poles show minimal temperature contrast. The thick atmosphere transports heat so efficiently through circulation and radiation that it homogenizes the surface temperature globally. This stands in stark contrast to Earth, where temperature varies dramatically with latitude, season, and time of day. On Earth, equatorial regions can reach 40 degrees Celsius, while polar regions drop to minus 50 degrees Celsius or colder. Venus has no such variation. The entire planet bakes at the same infernal temperature, day and night, equator and poles, year-round. As you ascend through the atmosphere, pressure and temperature both decrease, but not uniformly. The lower atmosphere, called the troposphere, extends from the surface to about 65 kilometers altitude. Within this zone, temperature drops relatively steadily with increasing altitude, following a steep lapse rate. At 10 kilometers altitude, the temperature has decreased to about 630 Kelvin and the pressure to 50 bars. At 20 kilometers, temperature reaches about 500 Kelvin and pressure drops to 20 bars. At 30 kilometers, temperature falls to 400 Kelvin and pressure to 10 bars. At 40 kilometers altitude, temperature is roughly 340 Kelvin and pressure about 4 bars. This steady decline continues until you reach the middle cloud layer. The clouds of Venus exist in 3 main layers between roughly 30 and 70 kilometers altitude. The lower cloud layer extends from about 47 to 52 kilometers. The middle cloud layer occupies 50 to 56 kilometers. The upper cloud layer stretches from 56 to about 70 kilometers. These clouds consist primarily of droplets of sulfuric acid with a concentration of about 75 to 85% sulfuric acid mixed with water. Sulfuric acid is a powerful acid, corrosive to most materials. The cloud droplets have diameters typically around 2 micrometers, forming a dense haze rather than distinct clouds with clear boundaries like Earth's water clouds. The clouds are so thick and extensive that they completely obscure the surface from any external view. Radar must penetrate the clouds to map the surface below. The sulfuric acid forms through a complex series of chemical reactions in the upper atmosphere. Solar ultraviolet radiation breaks apart carbon dioxide molecules through photodissociation, producing carbon monoxide and highly reactive atomic oxygen. This atomic oxygen reacts with sulfur dioxide, which is present in trace amounts, producing sulfur trioxide. Sulfur trioxide then combines with water vapor, also present in trace amounts, to form sulfuric acid. The reactions occur primarily above 65 kilometers, where ultraviolet penetration is strongest. Once formed, sulfuric acid droplets gradually settle downward through the cloud layers. As they descend and the temperature increases, the droplets eventually reach altitudes where the heat is sufficient to vaporize them, typically around 30 to 35 kilometers altitude. The sulfuric acid breaks back down into sulfur trioxide and water vapor, which rise again through convection, allowing the cycle to repeat. This creates a circulation of sulfur compounds within the atmosphere that maintains the cloud layers. Presence of sulfuric acid clouds has profound implications. On Earth, water clouds form through condensation when air cools and can no longer hold its water vapor. Clouds then produce rain, returning water to the surface and completing the water cycle. On Venus, the sulfuric acid clouds form a similar cycle, but the precipitation never reaches the ground. The phenomenon is called virga, where rain falls from clouds but evaporates in the hot air beneath before reaching the surface. Sulfuric acid rain falling from Venus's clouds evaporates completely by about 30 kilometers altitude, leaving a haze layer below the main clouds, but no surface precipitation. The surface humidity is less than 0.1%, extraordinarily dry despite the clouds above. At altitudes around 50 to 55 kilometers, Venus's atmosphere achieves conditions remarkably similar to Earth's surface. The temperature ranges from about 293 Kelvin to 310 Kelvin, which is 20 degrees Celsius to 37 degrees Celsius. The pressure is approximately 1 bar, the same as Earth at sea level. This zone, often called the habitable altitude or cloud layer habitable zone, represents the most Earth-like conditions found anywhere on Venus. A human in a properly designed suit could potentially survive at this altitude without extreme thermal protection or pressure compensation. Of course, you would still need oxygen to breathe and protection from the sulfuric acid clouds, but the basic temperature and pressure would not kill you instantly like surface conditions would. This habitable zone has led to proposals for floating colonies or research stations suspended in Venus's atmosphere, using balloons filled with breathable air, which would be less dense than the surrounding carbon dioxide and provide natural buoyancy. Above the cloud layers, in the upper atmosphere extending from 70 kilometers to over 150 kilometers, conditions change dramatically. The temperature initially continues to decrease above the clouds, reaching a minimum of about 160 to 170 Kelvin at around 90 to 100 kilometers altitude. This is the mesosphere, and it is bitterly cold despite the searing temperatures far below. The low temperature results from efficient radiative cooling to space, combined with minimal heating from the absorbed sunlight in this thin region. Above this altitude, in the thermosphere, temperature begins to rise again as absorbed solar ultraviolet and extreme ultraviolet radiation heat the rarefied gas. By 150 kilometers altitude, temperatures can exceed 300 Kelvin, and by 200 kilometers, thermospheric temperatures may reach 400 to 500 Kelvin, though the air density is so low that these high kinetic temperatures do not translate to significant heat content. The most bizarre aspect of Venus's atmosphere is its superrotation. Venus itself rotates incredibly slowly, taking 243 Earth days to complete one rotation, but the atmosphere does not follow the surface. The upper atmosphere, particularly around the cloud tops at 60 to 70 kilometers altitude, circles the entire planet in only 4 Earth days. Winds at this altitude reach velocities of 100 meters per second, or 360 kilometers per hour, or roughly 220 miles per hour. These are permanent hurricane-force winds that blow continuously around the planet, always from east to west in the same direction as the planet's slow rotation, but 60 times faster. This phenomenon, where the atmosphere rotates faster than the underlying planet, is called superrotation, and it is extremely rare. Within our solar system, only Venus and Saturn's moon, Titan, exhibit atmospheric superrotation on a global scale, though Earth's equatorial stratosphere shows weak superrotation. The mechanism driving superrotation remains incompletely understood despite decades of study. The phenomenon requires momentum to be transporting from the lower latitudes toward the poles and from the slower rotating surface upward to the faster rotating upper atmosphere. Several processes contribute. Thermal tides, heating patterns produced by solar radiation, create waves in the atmosphere that can transport momentum. Atmospheric waves, generated by the interaction of winds with topographic features on the surface, also play a role. The clouds themselves participate by absorbing and re-radiating solar energy in patterns that drive circulation. Computer models suggest that a combination of these mechanisms working together maintains superrotation, but the precise balance and relative importance of each mechanism remain topics of active research. Superrotation decreases with altitude below the cloud tops and increases with altitude above them up to a point. Near the surface, winds are sluggish, typically only a few meters per second or less. The dense, viscous atmosphere resists motion. Friction with the surface and the strong stratification of the lower atmosphere damp out large-scale flow. Surface winds are so weak that they transport little sand or dust, and erosion from wind is minimal compared to Mars or Earth. As you ascend through the lower troposphere, wind speeds gradually increase. By 30 kilometers altitude, winds reach about 10 to 20 meters per second. By 50 kilometers, winds accelerate to 50 meters per second. At 60 kilometers, approaching the cloud tops, winds reach 80 to 100 meters per second. Above 70 kilometers, wind speeds peak at about 100 to 120 meters per second, depending on latitude and local conditions. The superrotation is also differential with latitude. Equatorial regions rotate more slowly than mid-latitudes. At the equator, the atmospheric circulation completes its circuit in about 5 to 6 days. At mid-latitudes, around 45 degrees latitude, the circulation is fastest, completing in about 4 days. At high latitudes approaching the poles, the superrotation breaks down, winds decelerate, and a different circulation pattern emerges. The poles exhibit strange vortex structures, massive swirling storm systems that were revealed by spacecraft observations. These polar vortices are permanent features, though they vary in structure and strength. They show spiral patterns and complex morphology not fully understood. The polar regions experience downwelling, where air descends from higher altitudes, warming adiabatically as it compresses, creating warm spots at the poles despite receiving less solar energy than equatorial regions. Venus's atmosphere exhibits complex wave patterns. Gravity waves, large-scale undulations in atmospheric density and temperature, propagate through the atmosphere, transporting energy and momentum. Kelvin waves, planetary-scale waves that circle the planet, have been detected in temperature and cloud structure observations. These waves interact with the superrotation, sometimes reinforcing it, sometimes disrupting it. The atmosphere is not in steady state, but fluctuates on timescales from hours to years. Observations from different missions have shown variability in wind speeds, cloud patterns, temperature structure, and chemical composition, indicating that Venus's atmosphere is dynamic and constantly evolving. Lightning occurs on Venus, though it differs from Earth's lightning. Radio signals consistent with lightning discharges have been detected by several spacecraft. The exact mechanisms generating lightning remain unclear because Venus's clouds are not water-based like Earth's thunderstorms. On Earth, charge separation in water clouds driven by ice particle collisions produces the electric fields that lead to lightning. Venus's sulfuric acid clouds somehow generate charge separation sufficient to produce lightning, possibly through frictional charging of cloud droplets or chemical reactions within the clouds. The rate of lightning on Venus appears lower than on Earth, but the planet-wide coverage means lightning may be occurring somewhere on Venus at most times. The upper atmosphere contains an additional mystery. Observations in ultraviolet light show dark, irregular patches and streaks in the clouds, sometimes forming a Y-shaped pattern or chevron features. These dark regions absorb ultraviolet light strongly, contrasting with the brighter surrounding clouds. The identity of the ultraviolet absorber remains unknown despite decades of speculation. Proposed candidates include sulfur allotropes, iron chloride particles, or perhaps even microorganisms living in the clouds, though the latter is highly speculative. The absorber plays a significant role in Venus's energy balance by absorbing about 50% of the incoming solar energy. Without it, Venus's albedo would be much higher, and the planet might be cooler. Understanding what creates these dark markings is a key unsolved problem in Venusian atmospheric science. The atmosphere of Venus represents an extreme outcome of planetary evolution. It is a greenhouse run to completion, a carbon cycle interrupted and frozen, a sky turned to acid, winds that race around a world that barely turns. The atmosphere is simultaneously Venus's defining feature and its greatest barrier to exploration. It hides the surface from view, destroys spacecraft with heat and pressure, corrodes materials with acid, and presents navigation and communication challenges unlike any other world. Yet understanding this atmosphere is essential to understanding Venus, because the atmosphere controls the surface temperature, drives any geological activity, determines how the planet interacts with the solar wind, and preserves the chemical records of Venus's evolution. Every measurement of Venus's atmosphere adds a piece to the puzzle of how planets work, and what makes a world habitable or inhospitable. Chapter 6: The Surface of Venus, a World Resurfaced. For centuries, the surface of Venus remained completely hidden. The thick clouds that give Venus its bright appearance in Earth's sky also ensure that no telescope can see through them to the world beneath. Astronomers could observe cloud patterns, track atmospheric features, and measure atmospheric composition, but the solid surface, the actual rocky planet where spacecraft might one day land, remained unknown until the space age. Early speculation imagined everything from tropical swamps to barren deserts. The reality, when radar finally penetrated the clouds and landers transmitted images from the ground, proved to be a volcanic landscape unlike anywhere on Earth. A world resurfaced on a global scale within the last billion years, erasing most of its geological history and presenting scientists with a surface that is simultaneously ancient and strangely young. The surface of Venus is hot and relatively smooth. Radar mapping, primarily from NASA's Magellan mission in the early 1990s, revealed topography across 98% of the planet. Venus lacks the dramatic elevation differences seen on Earth. On Earth, ocean basins plunge to depths of over 10 kilometers below sea level, while mountain peaks rise 8 kilometers above sea level, a total relief of more than 18 kilometers. Venus shows much less variation. Most of the surface lies within a range of plus or minus 2 kilometers of the mean planetary radius. About 80% of Venus's surface consists of relatively flat volcanic plains with gentle rolling hills. These plains dominate the landscape, covering vast regions with solidified lava flows that extend for hundreds or thousands of kilometers. The plains appear relatively young based on their smooth texture and the density of impact craters, which suggests they formed within the last 300 to 600 million years. Impact craters provide crucial information about surface age. When asteroids or comets strike a planet, they create craters whose numbers accumulate over time. A heavily cratered surface like the Moon or Mercury is old, dating back billions of years because it has been exposed to impacts for a long time. A surface with few craters is young, meaning it has been recently resurfaced by volcanic activity or tectonics that erased older craters. Venus has approximately 940 identified impact craters distributed across its surface. This is far fewer than the Moon despite Venus being closer to the Sun where impact rates are higher. The distribution of craters on Venus is nearly random, showing no clustering or regional variations that would indicate some areas are much older than others. This uniformity suggests that the entire surface was resurfaced within a relatively short time interval geologically speaking. Crater counting and statistical analysis indicate a surface age between 300 million and 600 million years, with some estimates suggesting 500 million years as the most probable age. This means that sometime during this period, volcanic activity covered most or all of Venus with fresh lava, burying older terrain and resetting the crater accumulation clock. Since that time, Venus has been relatively quiet. The rate of volcanic activity declined dramatically after the resurfacing event, and the planet has been accumulating craters on this relatively stable surface ever since. The near-random distribution of craters indicates that resurfacing stopped quickly rather than continuing at a reduced rate, because ongoing volcanic activity would preferentially erase craters in volcanically active regions, creating age variations across the surface that are not observed. This global resurfacing event is one of the most puzzling aspects of Venus's geology. Why did the planet undergo such a catastrophic episode of volcanism? What triggered it? Why did it stop? And has it happened multiple times in Venus's history? The leading explanation involves Venus's lack of plate tectonics. On Earth, plate tectonics provides a continuous mechanism for heat to escape from the interior. Oceanic crust forms at spreading ridges, cooling the mantle beneath. Subduction at convergent boundaries carries cool crust back into the mantle, stirring it and promoting convection. This process operates continuously, allowing Earth's interior to cool steadily over billions of years. Venus, lacking plate tectonics, cannot cool its interior this way. Instead, heat from radioactive decay of elements in Venus's interior builds up over time. The planet operates in what is called a stagnant lid regime, where a strong, rigid lithosphere acts as an insulating blanket, preventing efficient heat loss. As heat accumulates beneath the stagnant lid, the mantle becomes hotter and less viscous. Eventually, the mantle becomes hot enough and buoyant enough to force its way through the rigid lithosphere. This triggers widespread volcanic eruptions across the planet as magma breaches the surface at numerous locations. The resulting volcanic activity floods vast areas with lava, resurfacing the planet and releasing accumulated heat. Once enough heat has been released, the mantle cools slightly, becoming more viscous and less buoyant. Volcanic activity declines, and the lithosphere solidifies into a new stagnant lid. The planet then enters another phase of heat buildup, lasting hundreds of millions of years until the cycle repeats. This cyclical model explains the uniform surface age and the apparent cessation of volcanism after the resurfacing event. Venus may undergo such events every 500 million to 1 billion years, making the planet's surface evolution episodic rather than continuous. Alternative hypotheses suggest that the resurfacing was not a single catastrophic event, but rather a period of elevated volcanic activity that gradually declined. According to this equilibrium resurfacing model, volcanic activity has been more or less continuous, but varies in intensity over time. The current low crater density could reflect ongoing but slow volcanic activity that erases craters at a rate matching their formation rate, maintaining equilibrium. This model has difficulty explaining the random crater distribution, however, because active volcanic regions should show fewer craters than inactive regions, and no such pattern is observed. Recent studies in 2023 suggested that energetic collisions early in Venus's history might have triggered long-lived volcanic activity that persisted for billions of years before finally declining to low levels within the last billion years. This model invokes giant impacts as the energy source driving prolonged volcanism rather than periodic mantle overturn. Regardless of the exact mechanism, the resurfacing erased most evidence of Venus's ancient past. If Venus had plate tectonics billions of years ago, as some studies suggest, the evidence was buried beneath kilometers of lava. If Venus had liquid water and oceans on its surface in the distant past, any geological features associated with water were obliterated. The current surface of Venus provides a window into the last few hundred million years, but tells us almost nothing about the first 4 billion years of the planet's history. This makes understanding Venus's evolution frustratingly difficult because the most critical period, when Venus may have transitioned from Earth-like to its current state, is hidden beneath the volcanic plains. Not all of Venus's surface consists of smooth plains. About 8% of the surface consists of tesserae, regions of highly deformed terrain showing intense fracturing and folding. Tesserae appear as bright, rough patches in radar images because their complex topography scatters radar signals strongly. The name comes from the Greek word for tiles or mosaics, reflecting the broken, tessellated appearance of these terrains. Tesserae rise above the surrounding plains, forming plateaus or isolated massifs. The largest regions include Ishtar Terra in the northern hemisphere and Aphrodite Terra near the equator. These highlands show evidence of compressional and extensional tectonics, with mountain ranges, rift valleys, and intensely fractured zones all jumbled together. The deformation suggests that tesserae experienced strong tectonic forces that no longer operate or operate only weakly on Venus today. Tesserae may represent the oldest visible terrain on Venus, surviving the global resurfacing by virtue of their high elevation or compositional differences that made them resistant to being buried by lava flows. Some researchers propose that tesserae are analogous to continental crust on Earth, formed through processes requiring water and partial melting to produce more silica-rich rocks than typical basalt. If tesserae are indeed more felsic, richer in silica, they would indicate conditions very different from Venus's current dry, basalt-dominated geology. Spectroscopic measurements from orbit have been inconclusive, but some observations hint at compositional differences between tesserae and the surrounding plains. Future missions with improved spectroscopy or in situ analysis could resolve this question, potentially revealing whether Venus once had processes analogous to continental crust formation on Earth. The volcanic features on Venus come in varieties not seen on Earth. Shield volcanoes, broad gentle domes built by repeated lava flows, are common and often cluster in groups called shield fields, where hundreds of small shield volcanoes occupy a single region. These shield fields cover large areas of the plains. Larger volcanic constructs rise thousands of meters above the surrounding terrain. Mart Mons, the tallest volcano on Venus, rises about 8 kilometers above mean planetary radius. Sif Mons and Gula Mons are other prominent volcanic mountains. These structures formed through repeated eruptions at fixed locations, building up massive piles of lava over time. Pancake domes are among Venus's most distinctive features. These are flat-topped volcanic domes, typically 10 to 100 kilometers in diameter and about 1 kilometer high, with steep sides and fractured tops. They appear to have formed when highly viscous lava erupted onto the surface and spread outward slowly before solidifying. The high atmospheric pressure on Venus may help explain pancake domes. On Earth, when viscous lava erupts, gas trapped in the lava expands explosively, fragmenting the lava into pyroclastic material. On Venus, the high surface pressure suppresses explosive eruptions, forcing even gas-rich viscous magma to erupt effusively as lava flows. This allows viscous lava to spread into dome shapes rather than fragmenting. Pancake domes are often found in groups near coronae and tesserae. Coronae are circular to oval structures unique to Venus, ranging from 150 to over 1,000 kilometers in diameter. A corona consists of a central elevated region surrounded by concentric rings of fractures and ridges. They form when hot mantle material rises as a plume, reaching the base of the lithosphere and pushing the surface upward into a broad dome. Volcanic eruptions occur at the top of the dome. Eventually, the plume weakens or the material spreads laterally and the dome subsides under its own weight. The subsidence creates the concentric fractures as the crust stretches and cracks. Many coronae show multiple episodes of uplift and subsidence, creating complex overlapping fracture patterns. Hundreds of coronae have been identified on Venus, providing evidence of mantle plume activity and convection beneath the stagnant lithosphere. Lava channels, some extending for thousands of kilometers, snake across Venus's plains. These channels formed when low-viscosity lava flowed across the surface, carving channels through thermal and mechanical erosion. Some channels are hundreds of meters deep and kilometers wide. The longest channel on Venus, Baltes Valleys, stretches over 6,800 kilometers, longer than the Nile River on Earth. Such extensive lava channels require enormous eruption rates sustained over long periods, indicating that Venus experienced truly massive volcanic events in its past. Rift valleys formed by extensional tectonics, where the crust pulls apart, cut across some regions. Beta Regio, a prominent highland, features a large rift valley system. Rift valleys on Venus resemble those on Earth in structure, but appear to be inactive currently. Mountain ranges formed by compressional tectonics also exist. Maxwell Montes in Ishtar Terra rises to about 11 kilometers above mean planetary radius, making it the highest point on Venus. Maxwell Montes shows evidence of intense compression, possibly similar to the processes that build mountain ranges on Earth through plate collisions, though the exact mechanism on Venus remains debated. The surface composition of Venus, as measured by Soviet Venera and Vega landers, is predominantly basaltic. Basalt is a common volcanic rock on Earth, formed by partial melting of the mantle and erupted at mid-ocean ridges and volcanic hotspots. The similarity of Venus's surface composition to Earth's oceanic crust suggests that both planets' mantles have similar composition and melting behavior. The basaltic nature of the plains supports the volcanic resurfacing model, as basalt flows easily and can cover large areas in relatively thin sheets. Some highland regions may have different compositions, possibly more felsic, but data is limited. The lack of plate tectonics on Venus profoundly affects its geology. Without subduction, crustal material cannot be recycled into the mantle. Without seafloor spreading, new crust cannot be continuously produced. The stagnant lid prevents the efficient heat loss and material cycling that characterizes Earth. This difference between Earth and Venus, despite their similar sizes and bulk compositions, remains one of the central mysteries of comparative planetology. Why did Earth develop plate tectonics while Venus did not? The leading explanation involves water. Water weakens rocks, reduces their melting points, and acts as a lubricant along faults and plate boundaries. Earth's oceans and hydrated minerals in the crust enable plate tectonics. Venus, lacking water, has a dry, strong lithosphere resistant to the stresses that initiate plate motion. If Venus lost its water early, as some evidence suggests, it may never have developed plate tectonics or may have lost it once the water disappeared. The surface of Venus today is hostile, hot, crushing, and apparently lifeless. It is also geologically fascinating, preserving a record of volcanic processes operating under conditions unlike anywhere else in the solar system. The global resurfacing event created a relatively uniform surface age, unusual for a planet billions of years old. The diverse volcanic features demonstrate the variety of eruption styles and magma compositions that occur on Venus. The tesserae hint at a more complex geological past that preceded the resurfacing. Understanding Venus's surface is essential to understanding the planet's evolution, its interior dynamics, and the factors that control tectonics and volcanism on rocky planets. Future missions will probe deeper into these mysteries, analyzing surface materials, monitoring for active volcanism, and searching for the clues to Venus's hidden past beneath the lava-covered plains. Chapter 7: Volcanic Landscape, Mountains and Magma. Venus is a world built by fire. Over 90% of its surface consists of volcanic features: lava flows, volcanic plains, shield volcanoes, calderas, and structures found nowhere else in the solar system. The planet lacks plate tectonics, the process that constantly recycles Earth's crust and creates diverse geological features through subduction, seafloor spreading, and continental collision. Instead, Venus's geology is dominated by volcanism on a scale that dwarfs anything seen on Earth. The volcanoes themselves are enormous. The lava flows stretch for thousands of kilometers. The volcanic structures come in varieties that reveal the unique conditions under which they formed, shaped by Venus's high surface temperature, crushing atmospheric pressure, and thick, rigid lithosphere. Understanding Venus's volcanic landscape provides insight into how heat escapes from the planet's interior, how magma behaves under extreme conditions, and what happens to a world where volcanism operates without the moderating influence of plate tectonics. Shield volcanoes dominate Venus's volcanic inventory. These structures form when fluid basaltic lava erupts repeatedly from a central vent, flowing outward in all directions and gradually building up a broad, gently sloped mountain. The name comes from their resemblance to a warrior's shield lying on the ground, on Earth. The Hawaiian Islands are classic examples of shield volcanoes, built by hotspot volcanism, where a stationary plume of hot mantle material erupts through the moving Pacific plate. Mauna Loa in Hawaii, the largest shield volcano on Earth, rises about 9 kilometers from the ocean floor and covers an area of approximately 5,000 square kilometers. It formed over hundreds of thousands of years through countless eruptions. Venus has over 1,600 large volcanic features identified from Magellan radar mapping, and the majority are shield volcanoes. Many of Venus's shields exceed Earth's largest volcanoes in size. Sif Mons, located in western Isla Reggio, rises about 2 kilometers above the surrounding plains and spans approximately 200 kilometers in diameter. Gyula Mons, also in western Isla Reggio, reaches about 3 kilometers in height. Mart Mons, the tallest volcano on Venus, towers approximately 8 kilometers above the mean planetary radius and stretches over 400 kilometers across its base. These dimensions make Mart Mons comparable to or larger than Olympus Mons on Mars, though Olympus Mons rises higher at about 21 kilometers. The difference reflects the lower gravity on Mars, which allows volcanic constructs to grow taller before collapsing under their own weight. The shield volcanoes on Venus often appear in groups called shield fields, where hundreds of smaller shields cluster together within a region spanning hundreds to thousands of square kilometers. These fields suggest prolonged volcanic activity with multiple vents operating over time. Some shield fields contain over 500 individual small shields, each 10 to 20 kilometers in diameter, packed closely together with their lava flows overlapping and intermingling. The clustering indicates that mantle upwelling beneath these regions provided magma to numerous vents rather than concentrating at a single point. The small shields within these fields likely formed relatively quickly, perhaps in a few hundred to a few thousand years each, and then became inactive as the volcanic focus shifted to neighboring vents. Basaltic composition of Venus's lava, confirmed by measurements from Soviet Venera landers, explains why the lava flows are so extensive. Basalt has relatively low viscosity when molten, allowing it to flow easily across gentle slopes and travel great distances before solidifying. On Earth, basaltic lava flows from Hawaiian eruptions can extend for tens of kilometers. On Venus, the flows commonly extend hundreds of kilometers, and some reach over 1,000 kilometers in length. The longest lava channel on Venus, Baltes Valleys, stretches approximately 6,800 kilometers, making it longer than the Nile River on Earth. This extraordinary length results from a combination of factors unique to Venus. First, the high surface temperature of 464 degrees Celsius means that erupting lava cools much more slowly than on Earth. On Earth, lava erupts at temperatures between 1,000 and 1,200 degrees Celsius and rapidly loses heat to the surrounding 20 degrees Celsius air, solidifying relatively quickly. On Venus, lava erupts at similar temperatures but loses heat to air that is already 464 degrees Celsius. The reduced temperature difference dramatically slows cooling, allowing lava to remain fluid for much longer. Second, the high atmospheric pressure may suppress gas escape from the lava. On Earth, dissolved gases in magma expand and escape as the magma reaches the surface, causing explosive eruptions or creating frothy, viscous lava that does not flow far. On Venus, 92 bars of pressure keep gases dissolved in the magma, preventing explosive eruptions and maintaining low viscosity. Third, Venus's lower surface gravity compared to Earth, about 90% of Earth's, slightly reduces the flow resistance, allowing lava to spread more easily. Lava channels on Venus show remarkable features. Many have levees, raised banks along the channel edges formed when the flowing lava spills slightly over the sides and solidifies, building up the banks higher with each episode. Some channels show braided patterns where the flow split around obstacles or topographic highs and then rejoined. Others show evidence of multiple flow episodes, with older solidified flows visible beneath younger flows. The channels typically originate at volcanic vents or fissures and extend downslope, following the terrain gradient. Some channels terminate in broad lava fans or flow fields where the lava spread out across flat plains. Others disappear under younger lava flows that buried them during subsequent volcanic episodes. Coronae are among Venus's most distinctive and enigmatic features. These quasi-circular to oval structures range from about 150 to over 2,500 kilometers in diameter, with most falling in the 300 to 500 kilometer range. A typical corona consists of a central elevated plateau surrounded by concentric ridges and fractures forming an annulus, a ring-like pattern. Many coronae show evidence of volcanic activity within the central plateau, including small shield volcanoes, lava flows, and calderas. The fracture patterns indicate both extensional and compressional tectonics, with concentric grabens, normal faults formed by extension, and ridges formed by compression. Over 740 coronae have been catalogued across Venus's surface, making them one of the most common large-scale tectonic features on the planet. Coronae form through the interaction of mantle plumes with the lithosphere. A mantle plume is a rising current of hot, buoyant rock from deep within the mantle. As the plume ascends, decompression causes partial melting, producing magma. When the plume reaches the base of the lithosphere, it pushes upward against the rigid outer layer, creating a dome at the surface. The uplift stretches the overlying crust, producing concentric normal faults and grabens around the margins as the crust extends. Magma generated by the plume erupts at the surface, forming volcanic features within the central dome. Eventually, the plume weakens or its buoyant material spreads laterally beneath the lithosphere. Without continued support from below, the dome subsides under its own weight. The subsidence creates compressional features as the crust collapses inward, forming ridges and thrust faults. The result is a corona with its characteristic annulus of deformation surrounding a central volcanic plateau. Recent research in 2025, using gravity and topography data from Venus missions, has revealed that many coronae show evidence of active or recent plume activity. About 70% of well-resolved coronae display gravity anomalies consistent with ongoing mantle plume processes beneath them. Some coronae show positive gravity anomalies indicating dense, hot material currently rising beneath the surface. Others show patterns suggesting that the crust has been modified by plume-induced subduction, where the edges of the lithosphere are pulled downward around the plume's margins. This finding suggests that Venus's interior is more active than the relatively young, uniform surface age would indicate. The volcanic resurfacing event 300 to 600 million years ago may have reset the surface crater count, but mantle convection and plume activity have continued, creating coronae and modifying the crust in ways that do not always produce visible surface changes. Pancake domes are flat-topped circular structures 10 to 100 kilometers in diameter and about 1 kilometer high, with steep sides and fractured tops. They appear to have formed from extremely viscous lava that erupted onto the surface and spread outward slowly, piling up rather than flowing far. The viscous lava may have been more silica-rich than typical basalt, similar to rhyolite or dacite on Earth. Alternatively, the lava may have been basaltic, but cooled and degassed enough during ascent to become highly viscous by the time it reached the surface. The high atmospheric pressure on Venus plays a critical role in pancake dome formation. On Earth, viscous silica-rich magma typically erupts explosively because dissolved gases expand violently as pressure drops during ascent. The explosions fragment the magma into ash and pyroclastic material rather than producing lava flows. On Venus, the 92 bar surface pressure suppresses explosive eruptions by keeping gases dissolved in the magma. Even highly viscous, gas-rich magma must erupt effusively, oozing out as thick lava that forms domes. Pancake domes often occur in clusters, with multiple domes grouped within a few hundred kilometers. They are commonly found near coronae and tesserae, suggesting associations with regions of high heat flow or compositional anomalies. The fractured tops of pancake domes indicate that the domes cracked as they cooled and contracted, or as continued pressure from magma injection from below stretched the solidified crust on top. Some pancake domes show flow fronts where the viscous lava advanced outward in lobes, creating a scalloped appearance around the dome's margins. The formation of pancake domes requires special conditions: viscous magma, effusive eruption style, and relatively flat terrain. All these conditions are met on Venus, but rarely occur together on Earth, making pancake domes essentially unique to Venus. Calderas, collapsed depressions formed when magma chambers beneath volcanoes empty and the overlying ground sinks into the void, are abundant on Venus. Calderas range from a few kilometers to over 100 kilometers in diameter. Some are circular, indicating collapse into a centralized magma chamber. Others are elongated, suggesting collapse along fissure systems where magma was distributed in dike-like bodies rather than concentrated in chambers. The largest calderas may have formed during massive eruptions that emptied huge volumes of magma onto the surface in relatively short times. The calderas often show concentric fractures and terraces where the collapse occurred in stages as different levels of the magma chamber drained. Many calderas are nested, with smaller calderas inside larger ones, indicating multiple episodes of magma chamber formation, eruption, and collapse over time. Volcanic plains cover approximately 80% of Venus's surface. These plains consist of overlapping lava flows that flooded low-lying areas and filled topographic depressions. Individual flows are often difficult to distinguish because they blend together, but where flow boundaries are visible, the flows appear thin and extensive, consistent with low-viscosity basaltic lava. The plains show varying degrees of deformation. Some plains are relatively smooth and undeformed, representing the youngest surfaces on Venus. Others are cut by wrinkle ridges, linear to arcuate compressional features that form when plains undergo slight horizontal compression, called causing the surface to buckle. Wrinkle ridges are common on volcanic plains throughout the solar system, including on Mars and Mercury, and their presence on Venus indicates that the plains experience tectonic stresses after solidification. Rift valleys, features formed by extensional tectonics where the crust pulls apart, cut across some of Venus's highland regions. Beta Regio, a prominent topographic rise, hosts a major rift system extending over 2,000 kilometers. The rift consists of a central graben, a down-dropped block bounded by normal faults, flanked by volcanic features including shield volcanoes and lava flows. The rift formed as hot mantle material rose beneath Beta Regio, uplifting the surface and stretching the crust. The extension created the faults, and magma exploited the fractures to reach the surface and erupt. Similar rift systems occur at Atla Regio and in the western part of Isla Regio. These rifts resemble rift valleys on Earth, such as the East African Rift, though Venus's rifts are not part of a global plate tectonic system, but rather represent local responses to mantle upwelling beneath isolated hot spots. Mountain ranges on Venus formed through compressional tectonics. Maxwell Montes, part of Ishtar Terra in Venus's northern hemisphere, rises about 11 kilometers above the mean planetary radius, making it the highest point on Venus. Maxwell Montes consists of a series of parallel ridges and valleys, indicating intense compression that folded and thrust-faulted the crust vertically. The mountain range extends over several hundred kilometers and shows structural complexity comparable to Earth's Himalaya mountains. The mechanism that formed Maxwell Montes remains debated. Without plate tectonics, Venus lacks the collisional process that builds Earth's greatest mountain ranges. Possible explanations include downwelling of cold lithosphere pulling adjacent crust downward and causing compression, or edge effects around crustal plateaus where differences in crustal thickness create horizontal stresses. The high elevation of Maxwell Montes indicates that it is supported by thickened crust or by dynamic support from mantle flow beneath. The evidence for ongoing volcanic activity on Venus remains circumstantial but suggestive. Several lines of evidence point toward recent or current volcanism. First, measurements of sulfur dioxide in Venus's atmosphere show variations over time. The Pioneer Venus orbiter detected elevated sulfur dioxide levels in the late 1970s, which declined over the following years. Sulfur dioxide is injected into the atmosphere by volcanic eruptions, and it reacts with surface rocks or photodissociates in the upper atmosphere, removing it on timescales of years to decades. The observed variations could indicate that a major eruption occurred shortly before Pioneer Venus arrived, and the sulfur dioxide gradually declined as removal processes worked. Alternatively, ongoing volcanic activity may inject sulfur dioxide episodically, creating fluctuations in atmospheric levels. Second, some volcanic features show characteristics consistent with extreme youth. Certain lava flows appear pristine in radar images, with sharp flow fronts and minimal deformation or modification. Statistically, given Venus's impact rate, one would expect at least some craters to overlap with the youngest volcanic features if those features formed millions of years ago. The absence of such overlaps on some features suggests they may be younger than the crater accumulation age would indicate. Third, transient thermal anomalies detected from orbit could represent fresh lava flows. Identifying active volcanism definitively requires observing an eruption in progress, capturing thermal infrared signatures of molten lava, or detecting seismic signals from volcanic tremors. Future missions equipped with sensitive infrared instruments and seismometers aim to confirm whether Venus's volcanoes still occasionally roar to life, or whether the planet has settled into dormancy following the Great Resurfacing event. Venus's volcanic landscape tells the story of a planet trying to cool its interior without the benefit of plate tectonics. The enormous volcanoes, the extensive lava plains, the thousands of individual volcanic constructs all represent pathways for heat to escape from the mantle to the surface. The coronae reveal mantle plumes pushing upward against the stagnant lid, deforming the lithosphere but not breaking it into mobile plates. The pancake domes demonstrate how Venus's atmosphere alters eruption styles, forcing even viscous magma to erupt effusively. The lava channels show how Venus's environmental conditions allow lava to flow farther and longer than anywhere else in the solar system. Every volcanic feature is a piece of evidence in the ongoing effort to understand how Venus evolved into the world we see today, a world where volcanism operates under the most extreme planetary conditions in the inner solar system. Chapter 8: The Soviet Conquest, Venera Missions. The Soviet Union achieved what no other nation has accomplished before or since. Between 1961 and 1984, the Soviets launched a series of spacecraft toward Venus that would ultimately land on the planet's surface, survive in the most hostile environment in the solar system long enough to transmit data, and return images showing the rocky terrain beneath the acid clouds. The Venera program, named from the Russian word for Venus, represented an extraordinary engineering achievement accomplished through persistence, innovation, and a willingness to learn from catastrophic failures. While the United States focused primarily on Mars and the Moon during the space race, the Soviets turned their attention to Earth's twin planet. The missions faced crushing atmospheric pressure, temperatures hot enough to melt lead, sulfuric acid that corroded materials, and communication challenges across millions of kilometers. Yet they succeeded where success seemed nearly impossible, and the data they returned transformed our understanding of Venus from speculation into hard-won knowledge. The first attempt came with Venera 1, launched on February 12, 1961. The spacecraft was designed as a flyby mission to test technology and gather data about Venus's environment. Venera 1 carried instruments to measure cosmic radiation, magnetic fields, and micrometeorite impacts during its journey. The spacecraft design incorporated pressure vessels, thermal protection, and systems that would become standard for later Venus missions. However, 7 days after launch, Venera 1 lost contact with Earth. The communication failure likely resulted from overheating of the orientation system, causing the spacecraft to drift out of alignment with its antenna no longer pointing toward Earth. Venera 1 passed within 100,000 kilometers of Venus on May 19, 1961, but without communication, it could transmit no data. The mission was a failure technically, but it provided valuable experience in designing spacecraft for interplanetary missions. Venera 2, launched on November 12, 1965, suffered a similar fate. The spacecraft successfully made the journey to Venus, but a thermal control failure caused its systems to overheat. Contact was lost before the flyby on February 27, 1966. Venera 3, launched just 4 days after Venera 2 on November 16, 1965, carried an entry probe designed to descend through Venus's atmosphere. The spacecraft reached Venus on March 1, 1966, and the probe separated and entered the atmosphere, becoming the first human-made object to reach another planet's surface. However, communication had already been lost before entry, so no data was returned. These early failures taught Soviet engineers harsh lessons about the thermal environment of space and the difficulty of maintaining spacecraft systems over multi-month missions. Venera 4, launched on June 12, 1967, achieved a breakthrough. The spacecraft successfully flew to Venus, and on October 18, 1967, it released an entry capsule that descended through the atmosphere by parachute. The capsule transmitted data continuously for 98 minutes, measuring temperature, pressure, and atmospheric composition during its descent. The measurements revealed that Venus's atmosphere was primarily carbon dioxide, far denser than Earth's atmosphere and much hotter than expected. Venera 4's instruments reported temperatures rising to about 540 degrees Kelvin and pressures reaching about 18 atmospheres before transmission ceased. Soviet scientists initially claimed that Venera 4 had reached the surface, but analysis of the data showed that the probe had failed about 25 kilometers above the surface, crushed by atmospheric pressure far exceeding design limits. The mission demonstrated that Venus was far more hostile than anyone had imagined. Venera 5 and 6, launched in January 1969, were designed as atmospheric probes with the knowledge that reaching the surface would require much stronger construction. Both probes descended successfully, transmitting data for 53 and 51 minutes respectively. They confirmed the extreme conditions found by Venera 4 and provided more detailed atmospheric composition measurements. However, both probes also failed at altitudes around 20 kilometers, destroyed by the combination of heat and pressure before reaching the surface. The data from these missions forced a complete redesign of future landers. Venera 7 marked a turning point. Launched on August 17, 1970, this spacecraft carried a heavily reinforced landing capsule designed to withstand pressures up to 180 atmospheres and temperatures up to 800 degrees Kelvin. The thick titanium pressure sphere housing the instruments was built to survive where previous probes had failed. On December 15, 1970, the descent capsule separated and entered the atmosphere. During descent, the parachute ripped, causing the probe to fall faster than planned for nearly 30 minutes before striking the surface at approximately 17 meters per second. Despite the hard landing, Venera 7 survived. For 23 minutes, it transmitted data from the surface of Venus, recording a temperature of 747 Kelvin and pressure of 90 atmospheres. The signal was weak and difficult to extract from noise, but it was there. Venera 7 became the first spacecraft to successfully land on another planet and transmit data from its surface. Venera 8, launched on March 27, 1972, improved on this success. It soft-landed on Venus's day side on July 22, 1972, and transmitted for 50 minutes. The mission carried instruments to measure light levels, demonstrating that enough sunlight penetrated the thick clouds to illuminate the surface with intensity comparable to an overcast day on Earth. Venera 8 also carried a gamma-ray spectrometer that analyzed the composition of the surface material directly beneath the lander, finding rocks similar to terrestrial granite or basalt. The success of Venera 8 confirmed that landing on Venus was possible and that instruments could function long enough to return valuable data. Venera 9 and 10, launched in June 1975, were ambitious dual missions. Each spacecraft consisted of an orbiter and a lander. The orbiters would study Venus from space while serving as communication relays for the landers. On October 22, 1975, Venera 9's descent capsule landed and began transmitting. For 53 minutes, the lander sent data, including the first image ever captured from the surface of another planet. The black and white panoramic photograph showed a rocky landscape strewn with angular slabs and boulders, definitively proving that Venus's surface was solid rock, not the liquid or dust some theories had suggested. 3 days later, Venera 10 landed and transmitted for 65 minutes, returning another panoramic image showing a different type of terrain with flatter, layered rocks. These images revolutionized planetary science by providing direct visual evidence of Venus's surface conditions. The images revealed landscapes that were surprisingly detailed. The lighting was dim but adequate, with visibility extending tens of meters to what appeared to be a horizon or distant terrain features obscured by atmospheric haze. The rocks showed sharp edges and flat surfaces, indicating relatively young geological ages with minimal weathering. Some rocks appeared to be layered, possibly sedimentary rocks formed from volcanic ash deposits. Others showed more massive structure, suggesting solidified lava flows. The absence of sand or fine-grained material surprised some scientists who expected wind erosion to produce extensive dust deposits. The high atmospheric density means that wind speeds would need to be extremely high to move even small particles, and surface winds on Venus are typically less than 1 meter per second, far too weak to transport material. The landscape preserved by Venera 9 and 10 appeared geologically young and largely unmodified since formation. Venera 11 and 12, launched in September 1978, focused on atmospheric science. Both landers transmitted data for over 90 minutes each after landing in December 1978, though technical problems prevented cameras from functioning. The landers detected what appeared to be lightning during descent, providing evidence for electrical activity in Venus's clouds. They also measured noble gas abundances, finding that Venus has different isotopic ratios compared to Earth, providing clues about how the planet formed and evolved. Venera 13 and 14, launched in October and November 1981, represented the pinnacle of Soviet Venus lander technology. Venera 13 landed on March 1, 1982, and survived for 127 minutes, far exceeding its design lifetime of 32 minutes. The lander returned the first color images from Venus's surface, showing a landscape of orange-brown volcanic rocks under a yellow-orange sky. The color images revealed detail invisible in black and white, variations in rock texture and composition, subtle color differences between rocks and soil, and the strange quality of light filtered through the thick atmosphere. Venera 13 also deployed a spring-loaded drilling arm that extracted a soil sample, analyzed it with an X-ray fluorescence spectrometer, and determined its composition resembled terrestrial basalt. Venera 14 landed 5 days later and operated for 57 minutes. It returned color images showing flatter, more weathered rocks compared to Venera 13's site. The lander also analyzed soil composition, obtaining similar results indicating basaltic composition. An unfortunate malfunction occurred when the camera lens cap fell off and landed directly under the soil sampling arm. The arm dutifully drilled into the lens cap and analyzed it, causing confusion until engineers realized what had happened. Despite this mishap, Venera 14 returned valuable data confirming the earlier findings and demonstrating that Venus's surface composition is relatively uniform across different landing sites. Venera 15 and 16, launched in June 1983, were dedicated radar mapping orbiters. They entered orbit around Venus in October 1983 and operated through July 1984. Using synthetic aperture radar, they mapped the northern hemisphere at resolutions between 1 and 2 kilometers, revealing large-scale features including mountains, valleys, volcanic structures, and tectonic zones. The maps provided the first detailed view of Venus's surface topography and geology, showing a complex world far different from expectations. The data from Venera 15 and 16 laid the groundwork for later missions and demonstrated that remote sensing could provide comprehensive geological information despite the cloud cover. The final Soviet Venus missions were Vega 1 and 2, launched in December 1984. These were hybrid missions targeting both Venus and Halley's Comet. Each spacecraft released a lander and an instrumented balloon before continuing toward the comet. The landers functioned for about 20 and 56 minutes respectively, analyzing soil and returning atmospheric data. The balloons, filled with helium, floated at altitudes around 54 kilometers, where temperatures and pressures were relatively benign. For about 46 hours each, the balloons drifted with Venus's winds while transmitting data on temperature, pressure, wind velocity, cloud structure, and light levels. The balloons traveled thousands of kilometers, providing the first measurements of Venus's atmospheric circulation from within the clouds themselves. They confirmed the high wind speeds associated with superrotation and discovered vertical wind variations that helped explain how momentum is transporting through the atmosphere. The engineering challenges faced by Venera missions were extraordinary. The landers had to survive launch, interplanetary cruise, atmospheric entry at speeds over 10 kilometers per second, descent through temperatures rising to hundreds of degrees, and finally hours on a surface hot enough to melt zinc while immersed in an atmosphere denser than water at the bottom of Earth's oceans. Every component had to be designed for these extremes. Electronics were placed in thick-walled pressure vessels filled with inert gas to maintain manageable internal temperatures and pressures. The pressure vessels were then surrounded by additional insulation. Materials were selected for their ability to withstand heat and resist corrosion from sulfuric acid. Batteries had to operate at high temperatures without failing. Mechanical systems like camera covers, drilling arms, and parachute releases had to function reliably after months in space, followed by entry heating and exposure to Venus's environment. The Venera program succeeded through persistence and willingness to learn from failures. Nearly every mission taught lessons that improved the next one. When probes were crushed by pressure, engineers built stronger pressure vessels. When thermal control failed, they redesigned cooling systems. When atmospheric composition proved different than expected, they updated instruments and models. The Soviet space program's approach emphasized launching multiple similar spacecraft to increase chances of success, accepting that some would fail. This strategy worked. Of 16 Venera spacecraft sent to Venus between 1961 and 1984, 8 successfully returned data from the surface, 2 mapped the planet from orbit, and 2 deployed balloons in the atmosphere. These successes came at the cost of numerous failures, but the accumulated knowledge was immense. No spacecraft has landed on Venus since Vega 2 in 1985, over 40 years ago. The Venera and Vega landers remain the only spacecraft ever to photograph Venus's surface directly, to touch its rocks, to analyze its soil, and to experience its environment firsthand. The images they returned, grainy and low resolution by modern standards, are treasures. They show a world humans cannot visit in person, a place so hostile that our most robust machines survive only minutes to hours before succumbing. The data they transmitted revolutionized understanding of Venus, confirming it as a volcanic world covered in basaltic rock, heated to extremes by a runaway greenhouse effect, and utterly different from Earth despite their similar sizes. The Soviet conquest of Venus stands as one of humanity's great exploratory achievements, demonstrating that with determination and engineering ingenuity, we can reach even the most forbidding places in the solar system. Chapter 9: American Eyes, Pioneer Venus and Magellan. While the Soviet Union focused on landing spacecraft on Venus's surface, the United States took a different approach, emphasizing orbital missions that could study the planet comprehensively over extended periods. American missions to Venus prioritized understanding the planet as a complete system: atmosphere, surface, interior, and environment. This strategy produced extraordinary results, particularly through 2 landmark missions. Pioneer Venus, which arrived in 1978, conducted the first detailed long-term study of Venus's atmosphere and environment. Magellan, which operated from 1990 to 1994, produced the most comprehensive map of Venus's surface ever created, revealing the planet's geological complexity in unprecedented detail. Together, these missions transformed Venus from a cloud-shrouded mystery into a world whose structure and processes we could begin to understand scientifically. The Pioneer Venus project consisted of 2 separate spacecraft launched in 1978. The Pioneer Venus orbiter launched on May 20, 1978, atop an Atlas Centaur rocket. The spacecraft was designed as a flat cylinder 2.5 meters in diameter and 1.2 meters high, with solar panels extending outward to provide power. It carried 17 scientific instruments totaling 45 kilograms, an impressive payload for atmospheric and environmental studies. The instruments included radar for mapping surface topography, ultraviolet spectrometers for studying the atmosphere and clouds, infrared radiometers for measuring temperature, magnetometers for detecting magnetic fields, plasma analyzers for studying the solar-wind interaction, and mass spectrometers for measuring atmospheric composition in the upper atmosphere. The orbiter arrived at Venus on December 4, 1978, and fired its rocket engine to enter an elliptical orbit with periapsis, the closest approach, at about 150 kilometers altitude, and apopsis, the farthest point, initially at about 66,000 kilometers altitude. The Pioneer Venus multiprobe launched on August 8, 1978, carrying a bus spacecraft and 4 atmospheric entry probes. The bus carried 2 mass spectrometers to sample the upper atmosphere during its descent before burning up. The 4 probes consisted of 1 large probe weighing 315 kilograms and 3 smaller probes weighing 90 kilograms each. The large probe, called Sounder, carried 7 scientific instruments including mass spectrometers, gas chromatographs, radiometers, nephelometers to study cloud particles, and atmospheric structure instruments. The 3 small probes, named North, Day, and Night based on their entry locations, carried simplified instrument packages focused on atmospheric structure and composition measurements. The probes were released in mid-November 1978, and all four entered Venus's atmosphere on December 9, 1978, at different locations to sample atmospheric variability. The multiprobe mission provided detailed vertical profiles of Venus's atmosphere from the upper regions down to the surface. Sounder, equipped with a parachute, descended slowly and transmitted data for 56 minutes before impact. One of the small probes, the day probe, survived impact and continued transmitting from the surface for over an hour, an unexpected bonus since the probes were not designed to function after landing. The measurements revealed the atmospheric structure in unprecedented detail. Temperature, pressure, and composition profiles showed how conditions changed with altitude. The instruments detected 3 distinct cloud layers between 47 and 70 kilometers altitude, confirming the multi-layered structure suspected from remote observations. The cloud particles were identified as primarily sulfuric acid droplets based on their optical properties. Below the clouds, the atmosphere was remarkably clear despite its density, with visibility potentially extending kilometers horizontally at some altitudes. The composition measurements revealed that Venus's atmosphere is 96.5% carbon dioxide and 3.5% nitrogen, with trace amounts of sulfur dioxide, water vapor, carbon monoxide, argon, neon, and other gases. The noble gas abundances, particularly neon and argon, provided crucial clues about Venus's formation and evolution. The isotopic ratios of argon indicated that Venus outgassed its atmosphere relatively quickly early in its history, different from the gradual outgassing that characterized Earth. The deuterium to hydrogen ratio measured by the mass spectrometers showed enormous enrichment compared to Earth, strongly suggesting that Venus had lost massive amounts of hydrogen to space over billions of years, consistent with the hypothesis of ancient water. The Pioneer Venus orbiter far exceeded its design lifetime. The mission was planned for 243 Earth days, equivalent to 1 Venus rotation, allowing complete coverage of the planet beneath the orbit. The orbiter continued operating for 14 years, finally entering Venus's atmosphere and burning up on October 8, 1992. During its extended mission, the orbiter made numerous discoveries. Radar mapping revealed major surface features, including the highland regions Ishtar Terra and Aphrodite Terra, large volcanic constructs like Maxwell Montes and Rift Valleys. The radar could not achieve high resolution because the antenna was small, and the technique was conventional radar rather than synthetic aperture radar, but it provided the first topographic map showing Venus's large-scale geology. The ultraviolet instruments studied cloud patterns and dynamics. Images taken in ultraviolet light revealed the mysterious dark markings that absorb ultraviolet radiation strongly. These Y-shaped and chevron features moved with the atmosphere, completing circuits around the planet in about 4 days, demonstrating the superrotation. By tracking individual features over time, scientists measured wind speeds at cloud top level and mapped the circulation patterns. The measurements confirmed that winds were fastest at mid-latitudes and decreased toward the equator and poles. The polar regions showed complex vortex structures that appeared as bright spots in ultraviolet images, indicating different cloud properties or clearing in the clouds, revealing warmer lower levels. The magnetometer measurements provided a definitive answer to the question of Venus's magnetic field. Venus has no intrinsic global magnetic field. The magnetometer detected no organized dipole field like Earth's. This absence was initially surprising given that Venus is similar in size and presumably has a metallic core like Earth. The lack of a magnetic field suggests either that Venus's core is not molten and convecting, or that the core does not convect rapidly enough to generate a dynamo, or that Venus's extremely slow rotation prevents dynamo action. The slow rotation hypothesis is favored by many scientists. Earth's magnetic field is generated by convection in the liquid outer core combined with rapid rotation that organizes the convection into patterns capable of generating magnetic fields. Venus rotates once every 243 days, far too slowly for rotation to significantly organize core convection. Without a magnetic field, Venus lacks the protective magnetosphere that shields Earth from the solar wind. The plasma instrument studied how the solar wind interacts with Venus's upper atmosphere. Without a magnetic field, the solar wind directly impacts the ionosphere, the electrically conducting layer of the upper atmosphere. The interaction creates an induced magnetosphere where magnetic fields are carried by the solar wind drape around Venus, forming a bow shock on the sunward side and a magnetotail extending downstream. The Pioneer Venus measurements showed that the solar wind penetrates much closer to Venus's surface than it does to Earth's surface, coming within a few hundred kilometers of the ground. This direct interaction strips atmospheric particles from the upper atmosphere, carrying ions away in the magnetotail and contributing to atmospheric loss over geological time. The measurements quantified the loss rates, showing that Venus loses hundreds of tons of atmosphere per day to solar wind stripping. Over billions of years, this process has removed significant atmosphere, though not enough to explain the complete loss of water by itself. The hydrogen escape associated with water photodissociation is much more important for long-term water loss. The orbiter also served as a platform for astronomical observations. Instruments monitored solar activity, detected gamma-ray bursts from distant cosmic explosions, and made ultraviolet observations of several comets that passed near Venus. The mission demonstrated that planetary spacecraft could contribute to broader astronomical science while fulfilling their primary objectives. The longevity of Pioneer Venus orbiter and the wealth of data it returned established it as one of NASA's most successful planetary missions, providing a foundation for understanding Venus that influenced all subsequent research. Magellan represented the next generation of Venus exploration. Named after the Portuguese explorer Ferdinand Magellan, who led the first expedition to circumnavigate Earth, the spacecraft's mission was to map Venus's surface at resolutions high enough to see geological details and understand the planet's tectonic and volcanic history. The mission originated in the late 1970s as the Venus Radar Mapper, but underwent numerous design changes and budget constraints before finally receiving approval in the mid-1980s. To save costs, Magellan was built using spare parts from other missions. The main body came from a spare Voyager spacecraft bus. The high-gain antenna was a spare from the Voyager program. The attitude control systems used hardware from other missions. This approach, while economical, required careful engineering to ensure the disparate components worked together reliably. Magellan launched on May 4, 1989, aboard Space Shuttle Atlantis during the STS-30 mission. The spacecraft was carried in the shuttle's cargo bay along with an inertial upper stage booster rocket. After release from the shuttle, the inertial upper stage fired, sending Magellan on a trajectory toward Venus. The 15-month journey ended on August 10, 1990, when Magellan fired its solid rocket motor to enter orbit around Venus. The orbit was highly elliptical, with a periapsis of about 295 kilometers and an apopsis of over 8,000 kilometers, inclined nearly perpendicular to Venus's equator in a polar orbit. This orbit allowed Magellan to pass over every part of Venus's surface as the planet rotated beneath it. The spacecraft carried a single scientific instrument, but it was sophisticated and powerful. The radar system operated at a wavelength of 12.6 centimeters and functioned in 3 modes: synthetic aperture radar, imaging, altimetry, and radiometry. Synthetic aperture radar is a technique that uses the motion of the spacecraft to simulate a much larger antenna. As Magellan flew along its orbit, the radar transmitted thousands of microwave pulses every second. Each pulse reflected off the surface below, and the returning echoes were recorded with precise timing. Because the spacecraft was moving, each part of the surface was illuminated by many pulses transmitted from slightly different positions. Ground computers processed these multiple observations to create images with effective resolution much finer than the physical antenna size would normally allow. Magellan achieved resolutions between 120 and 300 meters, depending on spacecraft altitude and surface characteristics, more than 10 times better than any previous Venus mapping. The altimetry mode measured surface elevation by timing how long radar pulses took to travel to the surface and return. The precise measurements allowed construction of topographic maps showing elevation variations with vertical accuracy of about 50 meters. Combined with the imaging data, the topography revealed the three-dimensional structure of Venus's geological features. The radiometry mode measured the natural microwave emissions from the surface. Different materials and temperatures emit microwaves at different intensities, allowing scientists to infer surface properties including roughness, composition, and temperature variations. Magellan began its primary mapping mission on September 15, 1990. Each orbit took 3 hours 14 minutes. During a portion of each orbit, as the spacecraft flew over Venus's surface at periapsis, the radar operated for 37 minutes, imaging a strip of terrain beneath the orbital track. Over the course of 243 days, one Venus rotation, the planet turned beneath Magellan's orbit, allowing the radar to image strips covering most of the surface. The first mapping cycle ended on May 15, 1991, with 83.7% of the surface mapped. The gaps occurred mainly at high northern latitudes where orbital geometry prevented coverage. The spacecraft returned 1,200 gigabits of data during the first cycle, more than all previous NASA planetary missions combined up to that time. Subsequent mapping cycles filled in gaps and obtained data from different viewing angles. The second cycle, conducted with the spacecraft pointing in the opposite direction, imaged the southern hemisphere and filled northern gaps. The third cycle focused on obtaining stereo coverage by viewing the surface from different angles, allowing creation of three-dimensional terrain models. By the end of mapping operations, in September 1992, Magellan had imaged 98% of Venus's surface. Only small regions near the North Pole remained unmapped due to orbital geometry constraints. The data revealed Venus's surface in stunning detail. The images showed a world dominated by volcanic features. Over 80% of the surface consisted of volcanic plains created by extensive lava flows. Hundreds of shield volcanoes, coronae, pancake domes, and calderas were identified and catalogued. The largest volcanoes rose kilometers above the surrounding terrain, while lava channels stretched for thousands of kilometers. The relatively uniform crater distribution confirmed that the surface was young, probably between 300 and 600 million years old. The tesserae, regions of highly deformed ancient crust, stood out in radar images as bright, complex terrain showing intense fracturing and folding. Mountain ranges, including Maxwell Montes, displayed compressional structures, while rift valleys showed extensional features. The diversity of geological features demonstrated that Venus, despite lacking plate tectonics, had complex and varied geological processes. After completing the mapping mission, Magellan conducted gravity measurements during several additional cycles. The spacecraft's radio signal was tracked precisely from Earth, allowing scientists to detect tiny changes in Magellan's velocity caused by variations in Venus's gravitational field. These variations revealed density differences in Venus's interior, indicating crustal thickness variations, the presence of dense material at depth beneath volcanic features, and the distribution of mass within the planet. The gravity data provided insights into Venus's internal structure and the dynamic processes driving surface volcanism. In 1993, Magellan performed the first test of aerobraking, a technique for adjusting a spacecraft's orbit using atmospheric drag. The spacecraft lowered its orbit periapsis into the upper fringes of Venus's atmosphere. Each time Magellan passed through periapsis, atmospheric drag slowed the spacecraft slightly, reducing the apopsis altitude and gradually circularizing the orbit. This maneuver required careful monitoring because too much drag could cause the spacecraft to burn up, while too little would not achieve the desired orbit change. The test succeeded, demonstrating that aerobraking could be used as a fuel-efficient method for orbit modification. This technique was later employed on Mars missions, including Mars Global Surveyor and Mars Odyssey. On October 12, 1994, after 4 years at Venus, Magellan was commanded to plunge into the atmosphere for a final experiment. Controllers sent commands lowering the orbit until atmospheric drag overwhelmed the spacecraft's ability to maintain control. Magellan descended through progressively denser atmosphere, transmitting data about atmospheric properties and spacecraft response until communication was lost. The spacecraft burned up in Venus's atmosphere, ending one of NASA's most successful planetary missions. The radar maps created by Magellan remain the foundation for all Venus geological research. They revealed a world unlike any other, shaped by volcanism, operating under conditions unique in the solar system, and they raised as many questions as they answered about how Venus works and why it evolved so differently from Earth. Chapter 10: Modern Reconnaissance, Venus Express and Akatsuki. The early 21st century saw renewed interest in Venus as planetary scientists recognized how much remained unknown about Earth's nearest neighbor. 2 missions launched by the European Space Agency and Japan's Space Agency brought new capabilities and perspectives to Venus exploration. Venus Express, operating from 2006 to 2014, conducted the most comprehensive long-term study of Venus's atmosphere ever attempted, revealing its dynamic nature and discovering unexpected phenomena. Akatsuki, which entered orbit in 2015 after a dramatic initial failure and recovery, provided the first detailed observations of Venus's meteorology, tracking atmospheric features continuously and uncovering the planet's weather patterns. Together, these missions demonstrated that Venus is not a static, unchanging world, but a dynamic planet with complex atmospheric circulation, possible ongoing geological activity, and mysteries that continue to challenge our understanding. Venus Express began as a proposal to reuse hardware from the Mars Express mission, applying similar technology to Venus at reduced cost and development time. The European Space Agency approved the mission in 2002, and construction proceeded rapidly. Spacecraft was built around a cube-shaped body about 1.5 meters on a side, with 2 large solar panels extending outward. 7 scientific instruments were mounted on the spacecraft, chosen to provide comprehensive atmospheric observations across multiple wavelengths and measurement techniques. The instruments included spectrometers covering ultraviolet, visible, and infrared wavelengths, a thermal imaging system, a magnetometer, plasma analyzers, and a radio science package. Venus Express launched on November 9, 2005, aboard a Soyuz Fregat rocket from Kazakhstan. The spacecraft followed an efficient trajectory, reaching Venus after a 5-month journey. On April 11, 2006, Venus Express performed an orbit insertion maneuver, firing its main engine to slow down and allow Venus's gravity to capture it. The spacecraft entered a highly elliptical polar orbit with periapsis at about 250 kilometers and apopsis at about 66,000 kilometers. This orbit configuration meant that Venus Express spent most of each 24-hour orbital period far from Venus, allowing observations of the planet as a whole, but also provided close approaches for detailed atmospheric measurements. The periapsis was positioned over Venus's North Pole, giving excellent views of the northern polar region and the atmospheric dynamics there. Venus Express began routine science operations in July 2006 after completing commissioning and calibration. The primary mission was planned for 2 Venus sidereal days, equivalent to 486 Earth days, ensuring complete coverage as Venus rotated beneath the spacecraft's orbit. However, the spacecraft remained healthy and productive, leading to multiple mission extensions. Venus Express ultimately operated for 8 years, gathering data continuously until December 2014, when propellant exhaustion forced mission controllers to end operations. The mission's first major discovery came immediately upon arrival. The Visible and Infrared Thermal Imaging Spectrometer instrument, known by the acronym VIRTIS, captured detailed infrared images of Venus's southern polar region. The images revealed a massive double vortex at the South Pole, a swirling atmospheric feature that changed shape dramatically over time scales of hours to days. Previous missions had glimpsed the polar vortex, but Venus Express provided the first high-resolution, continuous observations showing its structure and variability. The vortex appeared as a dark feature in infrared images because the air within it was warmer than surrounding regions, indicating downwelling where air descends from higher altitudes and compresses adiabatically, heating as pressure increases. The vortex structure shifted between multiple configurations. Sometimes it appeared as a single circular feature centered approximately on the pole. Other times it split into two distinct cores orbiting around the pole. Occasionally, it became highly distorted with arms or filaments extending outward. The variability indicated that the polar atmosphere was turbulent and chaotic, driven by complex interactions between the superrotating winds at mid-latitudes and the slower rotating air near the pole. The wind shear at the boundary between these regions created instabilities that distorted the vortex and generated wave activity. Understanding the polar vortex required analyzing thousands of images taken over years, revealing patterns in the chaos and constraining models of atmospheric dynamics. Venus Express conducted the first long-term monitoring of Venus's atmospheric composition. The spectrometers measured abundances of sulfur dioxide, water vapor, carbon monoxide, and other trace gases as functions of altitude, latitude, and time. The measurements revealed that sulfur dioxide concentrations varied significantly, sometimes by factors of several times, over periods of months to years. Since sulfur dioxide is primarily injected into the atmosphere by volcanic eruptions and is removed by chemical reactions on timescales of years, the variations suggested either that Venus experiences episodic volcanic eruptions or that atmospheric circulation patterns transport sulfur dioxide from lower levels where volcanoes inject it upward into the regions where spacecraft could detect it. The debate over whether the variations indicate active volcanism continues, but Venus Express provided the best evidence yet that Venus's volcanoes may occasionally erupt in the present day. Lightning on Venus was confirmed by Venus Express after decades of ambiguous detections. The spacecraft's magnetometer detected electromagnetic pulses characteristic of lightning discharges. The radio science package detected Whistler mode radio waves, signals produced when lightning-generated electromagnetic waves propagate through the ionosphere. The detections confirmed that lightning occurs on Venus, though the mechanisms remain mysterious. Venus's clouds are made of sulfuric acid rather than water, and the charging mechanisms that generate Earth's thunderstorms do not obviously apply. Proposed explanations include frictional charging of cloud droplets in strong winds, volcanic lightning from ash-laden eruption plumes, or chemical reactions that separate charges within the clouds. Venus Express data showed that lightning occurs more frequently on Venus than on Earth, with detections occurring regularly during every orbit, indicating that lightning is ongoing somewhere on Venus at essentially all times. The mission discovered an ozone layer in Venus's upper atmosphere at altitudes around 100 kilometers. Ozone on Earth forms when ultraviolet light breaks apart molecular oxygen, and the resulting atomic oxygen recombines with molecular oxygen to form ozone. Venus's atmosphere contains very little oxygen, but photodissociation of carbon dioxide by solar ultraviolet produces some atomic oxygen. This oxygen can create trace amounts of ozone through reactions similar to those on Earth. The ozone layer on Venus is extremely tenuous, millions of times thinner than Earth's ozone layer, but its discovery demonstrated that ozone can form in carbon dioxide atmospheres and provided insights into atmospheric chemistry on both Venus and Mars, which also has trace ozone. Temperature mapping by Venus Express revealed unexpected cold regions in the atmosphere. At altitudes around 125 kilometers, temperatures dropped to about 120 Kelvin, cold enough that carbon dioxide could potentially freeze into ice or snow particles. This possibility, while not definitively confirmed, suggests that Venus might experience carbon dioxide snow at high altitudes, though any snow would sublime back to gas as it fell into warmer lower layers. The cold temperatures also indicated that the upper atmosphere loses heat to space very efficiently, contrasting with the incredibly effective heat trapping in the lower atmosphere. The spacecraft monitored Venus's rotation rate by tracking surface features visible through infrared atmospheric windows. When images taken years apart were compared, surface features did not appear exactly where they should be based on Venus's known rotation period. The discrepancy indicated that Venus's rotation rate varies slightly over time, changing by several minutes over periods of years. The cause likely involves exchanges of angular momentum between the solid planet and the dense atmosphere. When atmospheric circulation patterns change, the atmosphere can speed up or slow down. Conservation of angular momentum requires that if the atmosphere speeds up, the solid planet slows down, and vice versa. Venus's thick atmosphere contains enough angular momentum that these exchanges produce measurable changes in the planet's rotation rate, a unique effect not seen on other planets. Venus Express also discovered that Venus's superrotation is speeding up. Measurements of cloud-top wind speeds made by tracking features in ultraviolet and infrared images showed that winds increased by about 30% between Pioneer Venus observations in the 1970s and Venus Express observations in the 2000s. The acceleration suggests that Venus's atmospheric circulation is not in steady state, but evolves over decades. The causes remain uncertain, but may relate to changes in solar heating patterns, variations in lower atmospheric properties, or long-term cycles in atmospheric circulation. Understanding why the superrotation speeds up requires longer time series of observations than currently exist. In 2014, after 8 years of operations, Venus Express began running out of propellant needed to maintain its orbit and orientation. Mission controllers conducted a final aerobraking campaign, lowering the orbit into Venus's upper atmosphere to gather data on atmospheric density at altitudes around 130 to 150 kilometers. The spacecraft made brief passes through the atmosphere, measuring drag and temperature before climbing back to higher altitude. This risky operation provided unique data on a poorly understood atmospheric region. Eventually, propellant depletion prevented further orbit adjustments. Contact with Venus Express was lost on November 28, 2014, and the mission formally ended in December 2014. The spacecraft likely entered the atmosphere and burned up shortly thereafter. Japan's Akatsuki mission, whose name means dawn in Japanese, experienced one of the most dramatic failures and recoveries in space exploration history. The spacecraft launched on May 20, 2010, carrying 6 cameras designed to image Venus at wavelengths ranging from ultraviolet to infrared. The mission concept focused on meteorology, treating Venus as a weather system and observing it continuously to understand atmospheric circulation, cloud formation, and weather patterns. Akatsuki was designed to enter an elliptical orbit that would provide views of the entire planet every few hours, allowing tracking of individual atmospheric features as they evolved and moved. The spacecraft reached Venus on December 7, 2010, and fired its main engine to slow down for orbit insertion. 9 minutes into the planned 12-minute burn, the engine malfunctioned. The spacecraft entered safe mode and the orbit insertion failed. Akatsuki flew past Venus and entered orbit around the Sun. Mission controllers assessed the situation and determined that the main engine was damaged, possibly by a ruptured fuel line or contamination. However, the spacecraft's smaller attitude control thrusters were functional. Engineers calculated a new trajectory that would bring Akatsuki back to Venus after 5 years of orbiting the Sun. On December 7, 2015, exactly 5 years after the initial failure, Akatsuki performed a second orbit insertion attempt using only its attitude control thrusters. The maneuver succeeded, placing the spacecraft into a highly elliptical orbit with a period initially over 10 days. Despite the non-ideal orbit, Akatsuki began science operations and immediately made discoveries. Just 3 hours after insertion, the infrared camera detected a massive bow-shaped stationary wave in Venus's atmosphere at the cloud tops. The feature extended 10,000 kilometers across, and remained in a fixed position despite surrounding winds moving at 100 meters per second. The wave appeared to be a gravity wave, an atmospheric oscillation similar to waves on water, generated by winds flowing over topographic features on Venus's surface. The fact that such a wave could remain stationary and extend through the entire atmospheric depth from surface to cloud tops indicated that the lower and upper atmospheres are coupled more strongly than previously thought. The discovery demonstrated that surface topography influences atmospheric circulation even at altitudes where superrotation dominates. Akatsuki's near-infrared cameras observed Venus through atmospheric windows, wavelengths where carbon dioxide absorbs less strongly, allowing observation of lower atmospheric levels. By tracking cloud silhouettes against the thermal glow from deeper levels, scientists measured wind speeds at altitudes between 50 and 60 kilometers. The observations revealed an equatorial jet, a band of enhanced winds encircling the planet at low latitudes. This jet moved faster than surrounding air and contradicted theoretical predictions. Atmospheric physics generally predicts that equatorial winds should be slower than mid-latitude winds due to conservation of angular momentum. Earth and Mars both show weak winds at the equator compared to mid-latitudes. Venus's upper atmosphere follows this pattern, but the lower atmosphere shows the opposite, with fastest winds at the equator. Explaining this equatorial jet requires mechanisms that can accelerate equatorial air preferentially, and current models struggle to reproduce the observations. The mission discovered streaky cloud patterns extending thousands of kilometers in Venus's nightside atmosphere. These features appeared as bright streaks in infrared images, indicating regions where air was descending and warming. Computer simulations suggested that the streaks form in regions of strong downwelling associated with large-scale atmospheric waves. The patterns changed over hours to days as atmospheric circulation evolved, demonstrating that Venus's atmosphere is highly dynamic, with weather systems forming, moving, and dissipating like weather on Earth, but operating under vastly different physical conditions. Akatsuki created three-dimensional maps of Venus's atmosphere by combining observations at different wavelengths, probing different altitudes. The maps showed temperature, pressure, and composition varying with altitude, latitude, and time. The data revealed that Venus's atmosphere undergoes global-scale oscillations with periods of days to weeks, possibly analogous to weather systems on Earth, but driven by different mechanisms. Understanding these oscillations and their relationship to superrotation remains a major goal of ongoing research. Contact with Akatsuki was lost on April 20, 2024, after more than 8 years of science operations. Despite multiple attempts to re-establish communication, no signal was received. The mission was officially declared ended in 2025. The spacecraft likely experienced a critical failure, possibly in its power or communication systems. Nevertheless, Akatsuki accomplished remarkable science during its extended mission, transforming our understanding of Venus's meteorology and demonstrating that long-term monitoring reveals phenomena invisible in snapshots. Venus Express and Akatsuki showed that Venus is a dynamic, evolving world. The atmosphere changes continuously on multiple timescales. Volcanic activity may be ongoing. The rotation rate varies. The superrotation accelerates. Lightning flashes constantly. Gravity waves ripple through the atmosphere, connecting surface and space. These missions proved that understanding Venus requires long-term observation, not just brief visits. They raised new questions while answering old ones. They demonstrated that Venus remains one of the most challenging and fascinating worlds in the solar system, a planet that refuses to yield its secrets easily, but rewards persistence with discoveries that illuminate not just Venus, but planetary processes throughout the universe. Chapter 11: The Mystery of Venus's Rotation. Venus spins in the wrong direction. While most planets in the solar system rotate counterclockwise when viewed from above the Sun's north pole, Venus rotates clockwise. This retrograde rotation is bizarre enough But Venus adds another peculiarity. The planet rotates so slowly that one complete spin takes 243 Earth days. Meanwhile, Venus completes one orbit around the Sun in only 225 Earth days. This creates the strange situation where a day on Venus, measured by how long it takes to rotate once relative to the distant stars, is longer than a Venus year. The planet's rotation is so slow that if you stood on the equator, assuming you could survive, you would be moving eastward at less than 2 meters per hour. A brisk walk would carry you faster than the ground beneath your feet rotates. Understanding why Venus rotates this way has puzzled scientists for decades, and the answer likely involves a complex history of massive impacts, gravitational interactions, and atmospheric forces acting over billions of years. The distinction between different types of days creates confusion that must be clarified. A sidereal day measures how long a planet takes to rotate once relative to the background stars. For Venus, this is 243 Earth days. If you marked the position of a distant star in Venus's sky and waited until it returned to exactly the same position, 243 Earth days would have passed. An orbital period or year measures how long the planet takes to complete one orbit around the Sun. For Venus, this is 225 Earth days. The planet travels around the Sun faster than it rotates, which is unusual but not impossible. However, a solar day, the time from sunrise to sunrise or noon to noon, depends on both the planet's rotation and its orbital motion. These two motions work against each other on Venus. Because Venus rotates retrograde, eastward toward the direction opposite its orbital motion, the combination produces a solar day much shorter than the sidereal day. After Venus rotates once relative to the stars, taking 243 days, the planet has moved significantly in its orbit. The Sun appears in nearly the same position in Venus's sky as it did before the rotation because orbital motion has compensated. To bring the Sun back to exactly the same position, Venus must rotate a bit further. The mathematics shows that one solar day on Venus equals approximately 116.75 Earth days. During one Venus year of 225 Earth days, the Sun crosses Venus's sky from east to west and returns to its starting position 1.92 times. A Venusian experiences about 1.92 sunrises and sunsets per year. This is the true measure of day and night as experienced on the surface. The retrograde rotation indicates that something dramatic happened to Venus. Planets form from rotating protoplanetary disks where material orbits the Sun in the same direction and rotation naturally emerges aligned with orbital motion. The angular momentum of the collapsing material should produce planets that rotate prograde, counterclockwise from the North Pole view. Venus either formed rotating prograde and was later reversed, or it slowed down so much during formation that its rotation stopped and then restarted in the opposite direction through some mechanism. Both scenarios require unusual circumstances, and identifying which occurred and how remains uncertain. The giant impact hypothesis proposes that Venus was struck by a massive object during the late stages of planetary formation. An impact with a planetary embryo roughly the size of Mars could have delivered enough energy and angular momentum to flip Venus's rotation. The impact would have been catastrophic, melting much of the planet and ejecting debris into space. Computer simulations show that impacts at specific angles and velocities can reverse a planet's spin. If the impactor struck Venus retrograde relative to the planet's initial rotation, the collision could cancel the original angular momentum and impart new rotation in the opposite direction. The violence of such an impact would have reset Venus's surface and possibly its interior structure, vaporizing rock and creating a global magma ocean that took millions of years to solidify. The giant impact hypothesis faces challenges. Most significantly, Venus has no moon. Earth's moon formed from debris ejected during the giant impact that created our planet's current rotation and tilt. If Venus experienced a comparable impact, where did the debris go? Several possibilities exist. The impact geometry might have been such that ejected material either escaped Venus entirely or fell back to the surface rather than forming a stable orbit. Alternatively, Venus might have formed a moon that later spiraled inward due to tidal interactions and crashed back into the planet. Venus's proximity to the Sun creates strong solar tides that could have destabilized a close moon's orbit. Without a moon to analyze, determining whether Venus experienced a giant impact requires indirect evidence, and such evidence remains ambiguous. Multiple impact scenarios suggest that Venus suffered not one, but several large impacts during formation. Some models propose that Venus initially rotated normally with a prograde spin and moderate rotation rate. A first giant impact could have slowed the rotation and tilted the planet's axis significantly. A second impact, occurring millions of years later, might have delivered the final retrograde push. This sequence of collisions could explain both the current slow retrograde rotation and the absence of a moon, if the timing and geometries prevented stable moon formation. Recent work in 2025 examining the possibility of giant impacts on Venus concluded that such events are consistent with the planet's current state, though proving they occurred requires more detailed modeling and additional observational constraints. Gravitational tidal interactions offer an alternative or complementary explanation. The Sun exerts gravitational tides on Venus that create bulges in the planet's crust and mantle. As Venus rotates, these bulges try to stay aligned with the Sun, creating friction that dissipates energy and exerts torque on the planet's rotation. Over billions of years, tidal friction can significantly alter a planet's spin. For Venus, solar tides tend to slow rotation and eventually drive the planet towards synchronous rotation, where one side permanently faces the Sun, similar to how the Moon is tidally locked to Earth. However, Venus has not reached synchronous rotation. Instead, it has settled into a slow retrograde state. Theoretical studies beginning in the early 2000s showed that Venus's rotation is consistent with a long-term evolution driven by solar tides and influenced by the planet's orbital eccentricity and obliquity, the tilt of its spin axis. The planet's spin can enter resonances, states where the rotation period matches some ratio of the orbital period. Venus appears to be in or near a 3:2 spin-orbit resonance in reverse. While the exact resonance ratios are complex, the key insight is that gravitational interactions with the Sun can naturally produce Venus's current rotation state given enough time. Computer simulations starting with a Venus that has a moderate initial tilt show that tidal evolution over billions of years drives the planet toward retrograde rotation without requiring any giant impact. Atmospheric thermal tides add another layer of complexity. Venus's thick atmosphere absorbs solar energy and heats up during the day. The heated air expands and creates pressure differences that drive winds. These winds exert torque on the solid planet below through friction at the surface. Because the atmosphere is so massive, 93 times Earth's atmospheric mass, the torque can be significant. Atmospheric thermal tides, the response of the atmosphere to solar heating patterns, create a repeating daily cycle of torque that acts on the planet's rotation. Depending on the atmosphere's properties and the planet's rotation rate, atmospheric tides can either speed up or slow down rotation. Research in the late 1990s and early 2000s showed that Venus's atmospheric tides exert a retrograde torque, meaning they push the planet to spin slower in the prograde direction or faster in the retrograde direction. Starting from a slow prograde rotation, atmospheric tides could drive the planet towards zero rotation and then into retrograde spin. Combined with solar gravitational tides, the atmospheric torque helps stabilize Venus in its current slow retrograde state. The atmosphere and the solid planet exchange angular momentum. When atmospheric superrotation speeds up, the solid planet slows down slightly to conserve total angular momentum, and vice versa. Venus express observations showing that the planet's rotation rate varies by several minutes over years provide direct evidence of this angular momentum exchange. The multi-stage history scenario combines impacts and tides. Venus likely formed with a prograde rotation typical of planets. Early in its history, one or more large impacts could have slowed this rotation and tilted the planet's axis. Then, over billions of years, gravitational and atmospheric tides continued to modify the rotation, gradually driving it toward the current retrograde state. This scenario incorporates both catastrophic early events and slow long-term evolution, potentially explaining features that neither mechanism alone addresses satisfactorily. The exact sequence and relative importance of impacts versus tides remain subjects of ongoing research and debate. The absence of a magnetic field connects to rotation. Earth's magnetic field is generated by the geodynamo, convection of liquid iron in the outer core, combined with the planet's rotation. The rotation organizes convective flows into patterns that generate magnetic fields through electromagnetic induction. Venus's slow rotation may prevent similar organization. Even if Venus has a liquid outer core with convection, the extremely slow spin might not impose enough Coriolis force to structure the convection into field-generating patterns. Some models suggest that Venus's core could still be molten, but that the rotation is simply too slow for dynamo action. Other models propose that Venus's core may have solidified completely, shutting down any possibility of a magnetic field regardless of rotation rate. Distinguishing between these scenarios requires measuring Venus's internal structure through seismic studies, which have not yet been conducted. The current rotation rate appears stable on human timescales, but variable on longer scales. Observations comparing Pioneer Venus data from the 1970s with Venus Express data from the 2000s show that the rotation period changed by about 6.5 minutes over roughly 30 years. This variation is attributed to angular momentum exchange with the atmosphere. When atmospheric circulation patterns change, perhaps due to variations in solar heating or internal atmospheric dynamics, the atmosphere speeds up or slows down. The solid planet responds by rotating slightly slower or faster to maintain total angular momentum. These exchanges happen continuously, causing the rotation period to fluctuate around an average value. Over millions of years, the average rotation might itself evolve if long-term changes in atmospheric mass or circulation occur. Venus's obliquity, the tilt of its spin axis relative to its orbital plane, is only 2.6 degrees. This is remarkably small compared to Earth's 23.5-degree tilt, which produces our seasons. Venus's near-zero tilt means the planet experiences almost no seasonal variation. The Sun remains nearly overhead at the equator year-round and stays near the horizon at the poles continuously. The small obliquity may result from tidal damping over billions of years. Gravitational tides from the Sun tend to reduce obliquity, pulling the spin axis toward perpendicular to the orbital plane. If Venus once had a larger tilt, either from its formation or from impacts, tides have erased it. The current small obliquity represents an equilibrium between whatever processes might increase tilt and the tidal damping that reduces it. The slow rotation affects Venus's environment and evolution. The lack of rapid rotation means no strong Coriolis effect to organize atmospheric circulation into the banded structures seen on Jupiter or the jet streams on Earth. Venus's superrotation, where the atmosphere circles the planet much faster than the solid surface, operates through different mechanisms than Earth's atmospheric circulation. The slow rotation allows the Sun to heat one side of Venus continuously for months at a time during the long solar day. However, the thick atmosphere distributes heat so efficiently that day-night temperature differences remain minimal. The slow rotation also means that any water Venus once had was not distributed efficiently between day and night hemispheres. If oceans existed, they would have absorbed sunlight for months, heating to high temperatures and evaporating extensively, potentially accelerating the runaway greenhouse. Understanding Venus's rotation illuminates planetary science broadly. Exoplanet surveys have discovered thousands of planets orbiting other stars, many of them close to their stars where tidal effects are strong. These planets likely experience tidal evolutions similar to Venus, but potentially more extreme. Many hot Jupiters and hot super-Earths are probably tidally locked with permanent day and night sides. Venus provides a nearby example of how tides and atmospheric interactions modify planetary rotations, helping us interpret observations of distant worlds where we cannot measure rotation directly, but can infer its effects on climate and habitability. The mystery of Venus's rotation remains incompletely solved. We know the planet spins slowly backward, taking longer to rotate once than to orbit the Sun, creating its peculiar calendar where years pass faster than days. We have plausible mechanisms involving giant impacts, gravitational tides, and atmospheric torques that could produce this state. We have observations showing the rotation rate varies slightly over decades. What we lack is definitive evidence determining which mechanisms actually shaped Venus's history. Did one massive impact flip the planet? Did slow tidal evolution gradually reverse its spin? Did multiple events combine to create the current state? Future missions carrying seismometers to measure Venus's interior structure, orbiters tracking rotation changes precisely over years, and improved computer models incorporating better understanding of Venus's atmospheric and interior properties will eventually answer these questions. Until then, Venus's backwards, sluggish spin stands as one of the solar system's most intriguing puzzles. Chapter 12: The Phosphine Debate and Search for Life. On September 14, 2020, an international team of astronomers announced one of the most controversial discoveries in planetary science history. Using telescopes in Hawaii and Chile, the team detected spectral signatures consistent with phosphine gas in Venus's atmosphere. Phosphine, a molecule consisting of one phosphorus atom bonded to 3 hydrogen atoms, is significant because on Earth it is produced almost exclusively by life or industrial processes. Finding it in Venus's clouds raised an extraordinary possibility. Could microbial life exist floating in the atmosphere of Earth's evil twin? The announcement triggered immediate scientific debate ranging from calm skepticism to heated criticism. Within weeks, other research teams challenged the detection itself, questioning whether the observed signal represented phosphine or something else. The controversy continues today, more than 4 years later, with no consensus reached. Whether phosphine truly exists on Venus remains uncertain. Whether Venusian clouds could harbor life remains speculative. But the debate has reinvigorated Venus research and forced scientists to confront how we search for life beyond Earth. The discovery team, led by Jane Greaves of Cardiff University, used 2 radio telescopes to detect phosphine. The James Clerk Maxwell Telescope in Hawaii made initial observations in June 2017, detecting an absorption feature at the wavelength where phosphine absorbs radiation. The signal was intriguing but required confirmation because radio observations can produce false signals from instrumental effects or data processing artifacts. The team obtained time on the Atacama Large Millimeter Array, a powerful radio telescope array in Chile consisting of 66 individual antennas working together. ALMA observations in March 2019 confirmed the absorption feature at the phosphine wavelength. The combined data from both telescopes provided evidence that phosphine existed in Venus's atmosphere at altitudes around 53 to 61 kilometers, within the middle and upper cloud layers, at a concentration of about 20 parts per billion. 20 parts per billion sounds tiny, but for phosphine on Venus, it represents an enormous abundance. Phosphine should not exist in Venus's atmosphere at detectable levels according to standard atmospheric chemistry models. Ultraviolet radiation from the Sun rapidly breaks apart phosphine molecules through photodissociation. Sulfuric acid in the clouds should destroy phosphine through chemical reactions. The oxygen present in trace amounts should oxidize phosphine. Even if some process produced phosphine continuously, the destruction rate should be so high that concentrations never build up to observable levels. Yet the observations suggested phosphine was present at concentrations thousands of times higher than predicted by models. Something was producing phosphine faster than it was being destroyed, or the destruction mechanisms were much less efficient than believed, or the observations were wrong. The announcement immediately sparked speculation about life. On Earth, phosphine is produced by anaerobic bacteria that live in oxygen-poor environments like swamps, wetlands, and the intestines of animals. These microorganisms generate phosphine through metabolic pathways involving reduction of phosphate compounds. Phosphine also appears in small quantities around industrial sites, produced as a byproduct of certain chemical processes, and in laboratory settings where chemists synthesize it intentionally. Apart from these biological and technological sources, Earth produces virtually no phosphine. Finding phosphine on Venus thus suggested either an unknown abiotic chemical process specific to Venus's environment or the presence of life producing it biologically as on Earth. The research team carefully avoided claiming they had discovered life. The published paper in Nature Astronomy stated that if no known chemical process could explain phosphine in Venus's atmosphere, then it must be produced by a process not previously considered plausible for Venusian conditions. That process could be unknown photochemistry, unknown geochemistry, or possibly life. The media coverage often emphasized the life angle more strongly than the scientists intended, leading to headlines announcing possible Venusian life. This created public excitement, but also contributed to backlash from scientists who felt the discovery was being oversold before independent verification. Within days of the announcement, criticism emerged. Some scientists questioned whether the observed signal truly represented phosphine. The spectral line observed by ALMA lay close to the wavelength where sulfur dioxide also absorbs radiation. Sulfur dioxide is abundant in Venus's atmosphere at variable concentrations, and subtle calibration errors or baseline subtraction issues in the data processing could potentially create an artificial signal at the phosphine wavelength. A team led by Geronimo Villanueva at NASA Goddard Space Flight Center reanalyzed the ALMA data and argued that sulfur dioxide contamination could account for the observed signal, with no phosphine required. They submitted their analysis to Nature Astronomy's Matters Arising section and suggested that the original team retract their paper, an unusually aggressive stance that intensified the controversy. ALMA staff discovered a calibration error in the data processing pipeline used for the original observations. When the data was reprocessed with corrected calibration, the phosphine signal weakened but did not disappear entirely. Greaves and her team reanalyzed their data using the corrected calibration and confirmed that a phosphine signal remained, though at a lower concentration of about 7 parts per billion rather than 20. They published an update acknowledging the calibration issue, but maintaining that phosphine detection was still valid. Other teams reanalyzed both the James Clerk Maxwell Telescope and ALMA data independently, with some concluding phosphine was present and others concluding the signal was too ambiguous or could be explained by sulfur dioxide. The debate revealed challenges inherent in detecting molecules through spectroscopy. Spectroscopy identifies molecules by their unique absorption or emission patterns at specific wavelengths. Each molecule has a spectral fingerprint determined by its quantum mechanical energy levels. However, fingerprints from different molecules can overlap, especially when observed at limited resolution or in complex environments like planetary atmospheres. Phosphine has a strong spectral feature around 1.1 millimeters wavelength in the radio spectrum. Sulfur dioxide has features at slightly different wavelengths, but close enough that with limited spectral resolution, or if sulfur dioxide concentrations are much higher than phosphine, the sulfur dioxide signal could be misidentified as phosphine. Resolving the ambiguity requires high spectral resolution observations, simultaneous observations of multiple spectral lines from both molecules, and careful modeling of atmospheric chemistry and structure. In 2023, follow-up observations using the James Webb Space Telescope aimed to clarify the situation. The infrared observations searched for phosphine signatures at different wavelengths. The results, published in 2024, found no evidence for phosphine, but did detect increased sulfur dioxide in Venus's mesosphere above the cloud tops at concentrations that varied with time. The observations suggested that the original ALMA detection could have been sulfur dioxide rather than phosphine. However, the JWST observations probed different altitude ranges and wavelengths than the original radio observations, making direct comparison difficult. Phosphine might exist at lower altitudes within the clouds where JWST cannot easily detect it, while sulfur dioxide dominates at higher altitudes where JWST observed. Alternatively, phosphine might never have existed, and the original signal was contaminated by sulfur dioxide variability. Independent research examined whether any abiotic chemical processes could produce phosphine on Venus. Teams modeled volcanic outgassing, lightning-induced chemistry, photochemistry driven by solar ultraviolet radiation, meteoric delivery of phosphorus compounds, and chemical reactions in sulfuric acid clouds. No known mechanism produced phosphine at the observed concentrations. Volcanism can release small amounts of phosphorus compounds, but these compounds quickly oxidize in Venus's atmosphere rather than forming phosphine. Lightning creates highly reactive chemical environments that might generate trace phosphine momentarily, but lightning frequency on Venus appears too low and phosphine destruction too rapid for buildup. Photochemistry and sulfuric acid cloud chemistry both destroy rather than create phosphine. The absence of plausible abiotic production mechanisms strengthened arguments for life, but also raised skepticism about whether phosphine was truly present. The possibility of life in Venus's clouds preceded the phosphine controversy by decades. In 1967, biophysicist Harold Morowitz and astronomer Carl Sagan published a paper discussing the potential habitability of Venus's atmosphere. They noted that while the surface was impossibly hostile, the cloud layer between 45 and 65 kilometers altitude had temperatures and pressures compatible with life. Water activity in sulfuric acid droplets could support metabolism if organisms adapted to highly acidic conditions. Earth hosts extremophiles, organisms living in extreme environments, including acidophils that thrive in pH 1 sulfuric acid mine drainage. If life could exist in such environments on Earth, perhaps it could exist in Venus's clouds. More recent habitability assessments focused on the lower cloud deck, where conditions are most Earth-like. At 50 to 55 kilometers altitude, temperatures range from 20 to 70 degrees Celsius, and pressure approximates 1 bar. Sulfuric acid droplets in this region are about 75% acid and 25% water. This is extremely acidic, far more acidic than any natural water body on Earth, but some terrestrial microorganisms tolerate sulfuric acid at comparable concentrations. The droplets contain sufficient water for biochemistry, assuming organisms could maintain cell integrity despite the acid. Ultraviolet radiation from the sun, while strong, is largely absorbed by the upper atmosphere before reaching the cloud deck. The clouds receive enough visible light for photosynthesis. Energy sources, including solar light, chemical gradients between atmospheric layers, and potentially sulfur-based metabolism exist. The life cycle challenge poses the greatest difficulty for Venusian life. Cloud droplets are not permanent. They form in the upper clouds through condensation, grow as water and sulfuric acid accumulate, and gradually settle downward under gravity. As droplets descend below about 40 kilometers altitude, rising temperatures evaporate them. Any organisms within the droplets would be carried downward into the hot lower atmosphere, where temperatures exceed 200 degrees Celsius, conditions that would destroy all known biochemistry. For a viable ecosystem, organisms must either reproduce fast enough to populate new droplets forming in the upper clouds before the old droplets carrying them are destroyed, or they must have a mechanism to escape sinking droplets and return to the clouds. One hypothesis proposes a life cycle involving desiccation-resistant spores. Organisms living in cloud droplets could produce spores as droplets descend and conditions become unfavorable. The spores, being lighter than the surrounding air or carried by updrafts, could remain suspended or be lofted back upward to altitudes where new droplets form. Spores would then rehydrate and germinate in fresh droplets, restarting the active phase of life. Earth organisms, including bacteria and fungi, use sporulation to survive harsh conditions, and spores can remain viable for years or centuries in dormant states. Venusian organisms would need to cycle between active and dormant phases repeatedly, perhaps multiple times per year, given the rapid sinking rate of cloud droplets. Alternative models suggest organisms coating the outsides of solid particles that remain suspended in the clouds long term. Sulfur particles and other aerosols exist in Venus's clouds at altitudes above the sulfuric acid cloud deck. These particles could provide stable surfaces where organisms establish colonies protected from the acid droplets below. The organisms could extract water and nutrients from the atmosphere and use solar energy for metabolism. Mode 3 particles, mysterious components of Venus's upper haze layer that absorb ultraviolet radiation strongly, have been speculatively identified as possible microbial colonies coated with UV protective pigments. This idea is highly speculative and faces challenges, including explaining how organisms obtain sufficient water and nutrients from the tenuous upper atmosphere. The sulfur-based metabolism hypothesis proposes that Venusian organisms might power their biochemistry through anaerobic photosynthesis using elemental sulfur instead of water. Earth's first photosynthetic organisms, appearing over 3 billion years ago, used hydrogen sulfide as an electron donor rather than water. Some modern bacteria continue using this metabolic pathway. Venus's atmosphere contains sulfur dioxide and elemental sulfur in various forms. Organisms could potentially reduce sulfur dioxide to elemental sulfur while oxidizing hydrogen sulfide or other reduced sulfur compounds, generating energy to fix carbon dioxide into organic molecules. This metabolism would not produce oxygen, consistent with Venus's oxygen-poor atmosphere, and could operate in the sulfur-rich Venusian environment. The origin of hypothetical Venusian life raises profound questions. If life exists in Venus's clouds, did it originate there or on the surface? If Venus once had surface oceans billions of years ago, as some evidence suggests, life might have originated in those oceans through processes similar to life's origin on Earth. When conditions deteriorated and the oceans evaporated, microorganisms might have migrated upward, adapting to life in cloud droplets as the only remaining habitable environment. This scenario requires that life evolved, established stable ecosystems, and then successfully transitioned from surface to cloud habitats over hundreds of millions of years. Alternatively, life might have originated directly in the clouds through chemical processes unique to that environment, though how prebiotic chemistry could occur in transient sulfuric acid droplets remains unclear. Panspermia, the hypothesis that life can spread between planets via meteorites or spacecraft, offers another possibility. Earth and Venus exchange material through impacts. Large asteroid strikes on Earth eject rocks into space, some of which eventually fall onto Venus. Similarly, Venusian material reaches Earth, though less frequently because escaping Venus's deeper gravity well requires more energy. If life originated on one planet and was transporting to the other, both could potentially harbor related organisms. Earth microorganisms could theoretically survive the journey through space and atmospheric entry if protected inside rocks. Whether they could survive Venus's environment upon arrival and establish populations is questionable, but not impossible to imagine for highly adapted extremophiles. Proving that life exists on Venus requires direct detection. Spectroscopic signatures like phosphine provide circumstantial evidence, but remain ambiguous and subject to multiple interpretations. Definitive proof requires either detecting organic molecules of clearly biological origin, observing life processes directly through microscopy of returned samples, or measuring biological signatures like specific metabolic products or isotopic fractionations characteristic of life. Future missions to Venus could collect atmospheric samples from the cloud layer and return them to Earth for detailed laboratory analysis. Instruments could analyze cloud particles in situ, searching for organic compounds, cell-like structures, or metabolic activity. Long-duration balloon missions could monitor atmospheric composition over months, tracking variations that might indicate seasonal or geographical patterns in biological activity. The phosphine debate, regardless of its ultimate resolution, demonstrates how difficult astrobiology is. Searching for life on other worlds requires extraordinary evidence and rigorous skepticism. Extraordinary claims, even when made by careful scientists using advanced instruments, must withstand intensive scrutiny. The controversy surrounding Venus phosphine illustrates the scientific process at work, contentious and sometimes unpleasant, but ultimately driving toward truth through repeated testing and independent verification. Whether phosphine exists on Venus remains undecided. Whether Venusian clouds harbor life remains unknown. But the questions have been raised, the hypotheses formulated, and future missions plan to seek answers. Venus has joined Mars and the icy moons of Jupiter and Saturn as a prime target in humanity's search for life beyond Earth, a remarkable development for a planet long dismissed as utterly sterile. Chapter 13: Future Missions Return to Venus. After decades of neglect following the Magellan mission, Venus is experiencing a renaissance. In June 2021, NASA announced the selection of 2 new missions to Venus, DAVINCI and VERITAS. These selections followed closely on the European Space Agency's June 2021 approval of Envision, making 3 major Venus missions planned for launch in the late 2020s and early 2030s. Additional missions from India's space agency, private companies, and international collaborations are also under development. This fleet of spacecraft will study Venus more comprehensively than ever before, investigating its atmosphere from cloud tops to surface, mapping geological features at unprecedented resolution, searching for active volcanism, and probing the planet's interior structure. The missions represent investments of billions of dollars and thousands of person-years of effort, driven by fundamental questions about why Venus evolved so differently from Earth, and what the planet can teach us about planetary habitability, climate change, and the diversity of worlds throughout the universe. DAVINCI, whose acronym stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging, will be the first atmospheric probe to enter Venus's atmosphere since the Soviet Vega missions in 1985 and NASA's Pioneer Venus Multiprobe in 1978. Mission concept centers on a heavily instrumented descent probe that will measure atmospheric composition, temperature, pressure, and winds as it falls through the atmosphere from the cloud tops to the surface. The descent will last approximately 1 hour, during which the probe will transmit data continuously to an orbiting spacecraft serving as a communication relay. The relay orbiter will also conduct remote sensing observations during multiple Venus flybys before and after probe delivery. The DAVINCI probe will be the first spacecraft in the 21st century to brave Venus's atmosphere. Scheduled for launch no earlier than 2031, the mission faces extraordinary engineering challenges. The probe must survive entry deceleration exceeding 250 times Earth's gravity as it slams into Venus's upper atmosphere at over 10 kilometers per second. Aerodynamic heating during entry will raise the probe's heat shield to temperatures exceeding 1600 degrees Celsius. After the initial entry phase, the probe will deploy a parachute at approximately 70 kilometers altitude and begin its slow descent. The parachute allows the probe to fall slowly enough that instruments can make detailed measurements, but the long descent time means prolonged exposure to increasing temperature and pressure. The probe carries a mass spectrometer to measure atmospheric composition with unprecedented precision. The instrument will detect noble gases including neon, argon, krypton, and xenon at abundances 1,000 times lower than previous measurements allowed. Noble gas isotopes provide crucial information about Venus's formation and atmospheric evolution. The ratios of different isotopes reveal whether Venus's atmosphere was delivered during planetary formation, outgassed from the interior over billions of years, or supplied by cometary impacts. The mass spectrometer will also measure isotope ratios of hydrogen, carbon, oxygen, and sulfur, constraining how much water Venus lost and through what mechanisms. A gas chromatograph will identify and quantify trace atmospheric constituents, including sulfur compounds, chlorine-bearing gases, and potential organic molecules. The instrument can detect compounds at concentrations as low as parts per trillion, sensitive enough to find exotic chemical species produced by volcanism, lightning, or hypothetically by life. A tunable laser spectrometer will measure water vapor, carbon monoxide, and hydrogen sulfide concentrations as functions of altitude, revealing how these gases are distributed vertically and whether patterns consistent with sources at the surface exist. These measurements directly address whether recent or ongoing volcanic eruptions inject gases into the atmosphere. The probe includes a suite of atmospheric structure instruments that measure temperature, pressure, and wind speed throughout the descent. Accelerometers track turbulence and atmospheric dynamics. The data will reveal the vertical structure of Venus's atmosphere in unprecedented detail, constraining atmospheric circulation models and identifying convective layers, stable regions, and zones of vertical mixing. Understanding atmospheric structure is essential for interpreting chemical measurements and for predicting how material moves between different altitude ranges. Perhaps most exciting, DAVINCI carries a camera called the Venus Descent Imager. The camera will photograph Venus's surface through atmospheric windows, near-infrared wavelengths, where carbon dioxide absorbs less strongly. The images will be taken during the last 20 kilometers of descent, after the probe drops below the main cloud layers. Resolution will improve as the probe descends, reaching approximately 1 meter per pixel just before impact. The descent will target Alpha Reggio, one of the Tesserae highlands, providing the first close-up geological images of these ancient, highly deformed terrains. The images may reveal whether Tesserae are compositionally distinct from the surrounding volcanic plains, potentially showing weathering patterns or rock textures indicative of different formation processes. The camera will provide context for understanding Tesserae geology, one of the greatest unsolved mysteries about Venus's history. The DAVINCI Relay Orbiter will conduct remote sensing observations during 2 flybys of Venus before releasing the probe and multiple flybys afterward. Instruments include ultraviolet and near-infrared spectrometers that will map atmospheric composition and cloud properties globally. The orbiter will search for temporal and spatial variations in sulfur dioxide, water vapor, and trace gases that might indicate volcanic activity or other dynamic processes. The UV spectrometer will study the mysterious ultraviolet absorber that creates dark patches in Venus's clouds, attempting to identify its composition. The near-infrared instruments will map thermal emission from the surface through atmospheric windows, potentially detecting temperature anomalies associated with recent lava flows. VERITAS, the Venus Emissivity, Radioscience, INSAR, Topography and Spectroscopy mission, will orbit Venus and map the planet's surface at resolutions more than 10 times better than Magellan achieved. The mission's primary instrument is VISAR, the Venus Interferometric Synthetic Aperture Radar, an X-band radar system operating at 3.2 GHz frequency with a wavelength of 9.4 centimeters. VISAR consists of 2 radar antennas separated by 3.1 meters. The 2 antennas work together to create interferometric observations, measuring the same surface areas from slightly different positions simultaneously. By analyzing how the radar signals differ between the 2 antennas, scientists can construct extremely precise topographic maps. VERITAS will map Venus's surface topography with horizontal resolution of 250 meters and vertical accuracy of 5 meters globally. Selected regions, covering about 25% of the planet, will be mapped at even higher resolution, down to 15-meter horizontal resolution. This represents an order of magnitude improvement over Magellan's best topography, which had resolution of several kilometers horizontally and uncertainties of tens of meters vertically. The improved topography will reveal small-scale geological features invisible in Magellan data, including detailed structures of volcanic vents, lava flow margins, fault scarps, and deformation patterns. Scientists will be able to construct 3-dimensional models of Venus's surface, showing fine details of mountains, valleys, and volcanic constructs. The radar imagery will have 30-meter resolution globally, comparable to the best Magellan images, but covering the entire planet uniformly. This will allow comprehensive geological mapping and identification of features too small or too subtle for Magellan to detect. The radar will also measure surface roughness and reflectivity, providing information about rock types and weathering. Different rocks scatter radar differently depending on their composition, density, and texture. By analyzing radar return characteristics, Scientists can infer whether areas are composed of fresh, smooth lava, rough, fragmental material, or weathered rocks. Compositional variations between tesserae and plains could emerge from these measurements, finally revealing whether tesserae represent ancient continental-like crust or simply older volcanic rocks. VERITAS carries a near-infrared spectrometer called the Venus Emissivity Mapper that will observe surface emission through atmospheric windows. The instrument will map temperature variations across the surface with precision of a few degrees Celsius. Recent lava flows would appear warmer than surrounding terrain, providing evidence for active volcanism if temperature anomalies are detected. The spectrometer will also measure surface emissivity, how efficiently rocks radiate thermal energy, which depends on mineralogy. Basalt, granite, and weathered rocks have different emissivities. Mapping emissivity variations will create a compositional map of Venus's surface, identifying regions with unusual or diverse mineralogy that warrant follow-up investigation. The mission includes a radio science investigation that will map Venus's gravity field with unprecedented precision. As VERITAS orbits Venus, ground stations on Earth will track the spacecraft's radio signal continuously. Variations in Doppler shift of the radio frequency reveal how Venus's gravity pulls on the spacecraft as it flies over regions with different mass distributions. By analyzing gravity anomalies, scientists can infer crustal thickness variations, the presence of dense material in the mantle beneath volcanic features, and the structure of impact basins. Gravity data, combined with topography, reveals whether mountains are supported by thick crust, as on Earth's continents, or by dynamic forces from mantle upwelling. This addresses fundamental questions about Venus's internal structure and how the planet transports heat from interior to surface. VERITAS will search for surface changes between Magellan observations in the early 1990s and VERITAS observations in the 2030s. Comparing images separated by over 40 years will reveal whether any volcanic features formed during that interval, whether lava flows appeared where none existed before, or whether landslides or other surface modifications occurred. Detecting changes would definitively prove that Venus remains geologically active. Even if no changes are found, the upper limit on resurfacing rate would constrain volcanic activity levels, helping determine whether Venus is currently dormant or merely erupting at rates too low to detect in 4 decades of observation. Envision, the European Space Agency's Venus mission, will launch no earlier than the early 2030s and arrive at Venus several years after launch. The mission is designed as a follow-on to Venus Express, carrying instruments that build on discoveries from that mission and address questions it raised. Envision will orbit Venus in a near-circular orbit at altitude around 220 to 540 kilometers, chosen to optimize radar and spectroscopy observations. The mission will operate for at least 4 Venus years, approximately 6 Earth years, providing long-term monitoring of atmospheric and surface properties. The VENSAR instrument, Venus Synthetic Aperture Radar, will operate in S-band at 3.2 GHz, the same frequency as VERITAS, though Envision will fly at lower altitude, providing complementary observations. VENSAR will focus on high-resolution studies of selected areas at 30-meter resolution, with subregions mapped at 10-meter resolution. These detailed observations will target specific geological features, including coronae, volcanic complexes, tesserae margins, and rift zones. The goal is to understand fine-scale structures and relationships between different geological units, addressing how features formed and evolved. VENSAR will also conduct change detection, comparing new observations with Magellan and VERITAS data to search for surface modifications. The Subsurface Radar Sounder, SRS, represents a breakthrough capability. SRS will transmit radio waves at frequencies between 9 and 30 MHz that penetrate Venus's surface and reflect from subsurface layers where material properties change. The reflected signals return to the spacecraft and reveal the depth and characteristics of buried layers. This technique, called ground-penetrating radar, has been used on Mars and Earth, but never on Venus. SRS will probe depths from tens of meters to potentially several kilometers, depending on surface properties and geological setting. The instrument will search for buried impact craters beneath lava plains, revealing whether the volcanic resurfacing event covered older heavily cratered terrain. It will investigate tesserae, searching for layered structures that might indicate sedimentary processes or multiple episodes of volcanism. SRS will profile lava flow thickness and extent, determining how much material erupted during major volcanic episodes. The VenSpec suite consists of 3 spectrometers covering ultraviolet to near-infrared wavelengths. VenSpec-M will map surface composition by observing thermal emission through atmospheric windows at multiple wavelengths. Different minerals emit different spectral patterns, allowing identification of rock types across the planet. The instrument will create the first global compositional map of Venus, identifying basaltic plains, potentially more silica-rich tesserae, and regions with unusual mineralogy that might represent ancient or exotic geological processes. VenSpec-H will conduct extremely high spectral resolution observations of atmospheric composition, measuring water vapor, sulfur dioxide, carbon monoxide, and trace gases with precision exceeding all previous missions. The instrument will search for temporal variations indicating volcanic outgassing or atmospheric circulation changes. VenSpec-U will monitor sulfur dioxide and the mysterious ultraviolet absorber in the upper clouds, tracking how these components vary with time and location. Correlating variations with geological features could reveal links between surface volcanism and atmospheric chemistry. Envision's radio science experiment will measure Venus's gravity field and rotation variations. By tracking the spacecraft's motion precisely and observing how Venus's gravity perturbs the orbit, scientists will map mass distribution within Venus more accurately than ever before. The measurements will constrain the size and state of Venus's core, determining whether it is liquid or solid. The rotation measurements will quantify how Venus's spin rate changes over years, confirming Venus Express findings and providing data to test models of atmosphere-solid planet angular momentum exchange. India's Venus orbiter mission, unofficially called Chakrayaan after the Sanskrit name for Venus, received government approval in November 2024 and is planned for launch no earlier than 2028. The mission will carry 16 Indian instruments plus international collaborations, totaling about 175 kilograms of scientific payload. The spacecraft will be launched aboard India's geosynchronous satellite launch vehicle Mark II rocket and will enter a highly elliptical orbit around Venus, with periapsis around 500 kilometers and apopsis initially around 60,000 kilometers. Over several months, orbital adjustments will lower the apopsis to optimize observations. The payload includes a synthetic aperture radar to map surface topography and geology, an infrared camera to study thermal emission and surface composition, spectrometers covering ultraviolet to infrared wavelengths for atmospheric studies, and instruments to analyze the ionosphere and solar wind interaction. International contributions include instruments from France, Russia, Sweden, and Germany, making Chakrayaan a globally collaborative mission. The mission's goals focus on understanding Venus's atmosphere and surface evolution, searching for active volcanism, and comparing Venus with Earth and Mars to understand why terrestrial planets evolved so differently. Rocket Lab, a private launch vehicle company, is partnering with the Massachusetts Institute of Technology to conduct the first privately funded interplanetary mission. The Venus Life Finder mission will send a small probe to Venus as early as 2026, years before the large government missions arrive. The probe will be tiny, carrying a single instrument to analyze cloud particles during a brief atmospheric entry. The instrument is designed to detect organic molecules or other chemical signatures that might indicate life in Venus's clouds. Because the mission is small and low cost, it serves as a pathfinder, demonstrating that private companies can conduct valuable planetary science. Follow-on missions with more capable payloads are planned if the first mission succeeds. Long-duration balloon concepts are being developed for future missions. A balloon floating at 50 to 60 kilometers altitude could operate for months or years in the relatively benign conditions of Venus's middle atmosphere. Solar panels on the balloon envelope would provide power. Instruments could sample cloud particles, measure atmospheric composition continuously, track meteorological phenomena, and monitor for volcanic plumes or other transient events. The balloon would drift with Venus's superrotating winds, circling the planet repeatedly and providing global coverage over time. Periodic altitude adjustments by venting gas or dropping ballast would allow vertical profiling and sampling at different levels. Several studies have developed balloon designs capable of surviving Venus's environment, including materials resistant to sulfuric acid and thermal systems to protect instruments from temperature variations. Sample return remains the ultimate goal. Bringing pieces of Venus's atmosphere, clouds, or surface back to Earth would allow laboratory analyses impossible with spacecraft instruments, revealing chemical and isotopic details that would definitively answer questions about Venus's history and potential habitability. Atmospheric sample return is difficult but feasible with current technology. A small probe could collect gas or cloud particles in sealed canisters, ascend back through the atmosphere on a rocket, rendezvous with an orbiting return vehicle, and journey back to Earth. Surface sample return poses extraordinary challenges. Operating on the surface long enough to collect samples requires systems that survive for hours at 464 degrees Celsius and 92 bars pressure. Lifting samples from the surface to altitude where a rocket can launch requires aircraft or balloons capable of operating in the dense hot lower atmosphere, technologies that do not yet exist. Various concepts have been proposed, including high-temperature aircraft, balloons that inflate rapidly and ascend before overheating, or rovers that cache samples for later pickup. All require significant technology development before implementation. The 2030s will see a transformation in Venus science comparable to the Magellan era. Multiple spacecraft operating simultaneously will provide complementary observations that individual missions cannot achieve. DAVINCI will measure atmospheric chemistry in situ, while VERITAS and Envision map surface geology from orbit. The missions will coordinate observations, with orbiters monitoring regions where DAVINCI descends and searching for geological context for atmospheric measurements. Data will be shared among mission teams and with the broader scientific community, enabling integrated analyses that leverage all available information. This coordinated approach will address interconnected questions about Venus's geological activity, atmospheric evolution, interior structure, and potential habitability more effectively than isolated missions ever could. The next 2 decades promise to revolutionize our understanding of Venus. Questions that have persisted for 50 years will finally receive answers. Whether Venus has active volcanoes will be determined by detecting fresh lava flows or volcanic gases. What tesserae are made of will be revealed by compositional mapping and high-resolution imaging. Whether Venus once had plate tectonics will be constrained by subsurface radar revealing buried structures. How Venus lost its water will be illuminated by precise isotope measurements. Whether life could exist in Venus's clouds will be tested by searching for organic molecules and biological signatures. Venus is transitioning from a planet observed in isolation during brief missions to a planet under continuous study by an international fleet of spacecraft. The knowledge gained will inform not just Venus science, but comparative planetology, exoplanet research, and our understanding of how worlds evolve and what makes planets habitable or hostile to life. Chapter 14: Venus's Far Future. Venus, as we see it today, is not the end state. The planet will continue to evolve over billions of years, though the changes will be slow by human standards and subtle compared to the dramatic transformation from potentially habitable world to inferno that occurred in Venus's past. The future evolution of Venus is determined by 3 main factors: continued loss of atmosphere to space, the gradual brightening of the sun as it ages, and eventual catastrophic changes when the sun leaves the main sequence and becomes a red giant. Understanding Venus's far future requires extrapolating known physical processes forward through timescales longer than human civilization has existed, into epochs when Earth itself will be unrecognizable and humanity, if it still exists, will have spread beyond the solar system or ceased to exist entirely. Venus's fate is sealed by astronomy and physics operating on cosmic scales, and while we cannot predict every detail, the broad outlines are clear. Atmospheric escape continues today and will persist for billions of years. Venus loses hydrogen, helium, and heavier atoms from its upper atmosphere through multiple mechanisms. Thermal escape, also called Jean's escape, occurs when atmospheric atoms move fast enough to exceed Venus's escape velocity. Hydrogen, with its low mass, escapes thermally at rates of about 2 × 10⁻27 atoms per second. Helium escapes more slowly but steadily. Heavier atoms and molecules like oxygen, nitrogen, and carbon dioxide are too heavy for thermal escape at Venus's temperatures, but can be removed through other mechanisms. Photochemical escape involves ultraviolet radiation breaking apart molecules, with the resulting fragments sometimes gaining enough energy to escape. Sputtering occurs when solar wind ions strike atoms in the upper atmosphere, transferring momentum and ejecting them to space. Ion pickup happens when atmospheric ions are accelerated by electric fields associated with solar wind interaction and dragged away. The cumulative atmospheric loss rate, summing all mechanisms and all species, is roughly several hundred tons per day. This sounds substantial, but compared to Venus's total atmospheric mass of approximately 4.8 × 10⁻20 kilograms, the loss rate is negligible on human timescales. Venus would require several billion years to lose a significant fraction of its current atmosphere at present rates. However, loss rates are not constant. They depend on solar activity, particularly the solar wind intensity and ultraviolet flux. As the sun ages, it becomes more active in certain ways. The solar wind strengthens, ultraviolet emission increases. These changes will accelerate atmospheric escape in Venus's future. The Sun is currently about 4.6 billion years old and approximately halfway through its main sequence lifetime. As hydrogen in the Sun's core is converted to helium through nuclear fusion, the core gradually becomes denser and hotter. Higher temperatures accelerate fusion rates, causing the Sun to gradually brighten. Currently, the Sun brightens at roughly 1% per 100 million years. Over the next billion years, the Sun will become about 10% brighter than today. Over 2 billion years, 20% brighter. This brightening increases the solar energy Venus receives, driving surface temperatures even higher. The greenhouse effect on Venus is already so extreme that small increases in solar input do not dramatically change surface temperature. The thick atmosphere is so opaque to infrared radiation that almost no heat escapes from the surface regardless of temperature. The increased energy mostly heats the atmosphere and accelerates photochemical reactions and atmospheric escape, rather than heating the surface significantly. As the Sun brightens and solar wind strengthens, atmospheric escape from Venus will accelerate. Models predict that over the next several billion years, Venus could lose a substantial fraction of its atmosphere, perhaps tens of percent of the current mass. The atmosphere will become thinner and less dense. Surface pressure might decline from 92 bars to 70 or 60 bars over several billion years. This reduction would make the surface slightly less hostile, lowering the crushing pressure somewhat, though temperatures would remain extreme. The atmospheric composition will change gradually as different gases escape at different rates. Hydrogen continues escaping preferentially, further enriching the residual atmospheric deuterium. Oxygen produced by water photodissociation is too heavy to escape efficiently, so any remaining water vapor will be stripped of hydrogen while oxygen accumulates or reacts with surface rocks. Carbon dioxide, the dominant atmospheric component, escapes very slowly because its molecular weight is high, so the atmosphere will remain carbon dioxide dominated. Volcanic outgassing might partially replenish lost atmosphere if Venus remains geologically active. Volcanoes release carbon dioxide, sulfur dioxide, water vapor, and other gases from the interior. If outgassing rates match or exceed escape rates, atmospheric mass could remain stable or even increase. However, Venus's level of volcanic activity is uncertain, and many models predict declining activity as the planet's interior cools. Radioactive decay heat, which drives mantle convection and provides energy for volcanism, decreases exponentially with a time constant of billions of years. Venus's interior is cooling, and eventually volcanic activity will cease entirely, cutting off the source of new atmospheric gases. Once outgassing stops, atmospheric escape will gradually thin the atmosphere over billions of years. Approximately 6 to 7 billion years from now, the Sun will exhaust hydrogen in its core. Core fusion will cease, and the Sun will begin fusing hydrogen in a shell surrounding the helium core. This shell-burning phase causes the Sun to expand dramatically. The Sun will leave the main sequence and become a red giant star, increasing in radius by factors of hundreds. The outer layers of the Sun will cool, giving the star a reddish color, but the total luminosity will increase by factors of thousands. The Sun will swell beyond Mercury's orbit, possibly beyond Venus's orbit, potentially engulfing both planets. Whether Venus survives depends on complex interactions between the expanding solar envelope and the planet's orbits. As the Sun expands, it loses mass through a strong stellar wind. The outer layers of the red giant are loosely bound and blow away into space at rates of millions to billions of tons per second. This mass loss causes the Sun's gravitational pull to weaken slightly, and planets respond by moving outward to larger orbits. Whether planets move outward fast enough to avoid being engulfed depends on how quickly the Sun expands versus how quickly planets' orbits expand. Current models are uncertain, with some predicting that Mercury will be consumed, but Venus will survive in a wider orbit just beyond the solar photosphere, while other models predict both planets will be destroyed. If Venus is engulfed by the Sun's expanding envelope, the planet will spiral inward through friction with the hot gas, gradually losing orbital energy. The inward spiral accelerates as Venus descends into denser regions of the solar envelope. Atmospheric drag heats the planet to temperatures of thousands of degrees, vaporizing the atmosphere and surface. Rock and metal boil into gas, mixing with the solar envelope. Within perhaps a few thousand years of entering the envelope, Venus would spiral all the way into the Sun's core and be completely destroyed, its atoms mixed into the star's interior and eventually ejected through the stellar wind. Nothing would remain. Venus's 4.6 billion-year existence would end in final annihilation, every atom that ever formed the planet scattered into interstellar space. If Venus survives engulfment by moving outward to an orbit beyond the Sun's photosphere, the planet will experience conditions almost as extreme as destruction. The Sun's red giant photosphere has temperatures around 3,000 to 4,000 Kelvin. Venus orbiting just outside the photosphere would be heated by intense thermal radiation to surface temperatures potentially exceeding 2,000 Kelvin, hot enough to melt rocks completely. The planet would become a molten sphere of liquid rock and metal, a magma ocean covering the entire surface and extending deep into the mantle. The atmosphere, already subject to billions of years of gradual loss, would be stripped away completely by the intense radiation and stellar wind from the red giant. Venus would be reduced to a bare molten rock ball orbiting a dying star. Eventually, after roughly 1 billion years as a red giant, the Sun will shed its outer layers completely, ejecting them as a planetary nebula, a glowing shell of gas expanding into space. The remaining core of the Sun will become a white dwarf star, an Earth-sized ember glowing with residual heat, but no longer generating energy through fusion. The white dwarf will have perhaps half the Sun's current mass compressed into a volume about the size of Earth, with a surface temperature initially around 100,000 Kelvin that cools over billions of years. Venus, if it survived, will orbit this white dwarf remnant. The planet will gradually cool as the white dwarf dims. Over tens of millions of years, surface temperatures will drop below the melting point of rocks, and the magma ocean will solidify into a new crust. The planet will become geologically dead, its interior cooled below the point where convection or volcanism can occur. This far future Venus will be a dark, cold, airless rock orbiting a faint white dwarf. No atmosphere will remain. Surface temperatures will eventually drop to near absolute zero as the white dwarf fades and radiates progressively less heat. The surface will be frozen solid, covered perhaps in exotic minerals that condense from gases released when the magma ocean solidified. Impact craters will slowly accumulate as occasional asteroids or comets strike the lifeless surface. Venus will resemble a large asteroid or Mercury, geologically inactive, atmospherically barren, and utterly dead. This state will persist for trillions of years, longer than the current age of the universe, until the white dwarf cools to a black dwarf, a theoretical final state where the stellar remnant has radiated away all its thermal energy and become the same temperature as the cosmic microwave background. At that point, billions of trillions of years in the future, Venus will orbit a dead star in a dying universe, one of countless frozen rocks drifting through the darkness of space. Could Venus ever be terraformed, transformed into an Earth-like habitable world? The challenges are almost incomprehensible. Venus's atmosphere contains some 400 times more carbon dioxide than Earth's entire atmosphere. Removing this carbon dioxide would require processing the entire atmosphere and somehow sequestering or ejecting the carbon. One proposed method involves solar shades, giant mirrors or occulters placed at the Sun-Venus Lagrange point to block sunlight from reaching Venus. With reduced solar heating, the atmosphere would cool dramatically. Carbon dioxide would rain out and potentially freeze onto the surface as dry ice. Over centuries to millennia, the surface would accumulate thick deposits of frozen carbon dioxide. Eventually, enough carbon dioxide could be sequestered as ice that atmospheric pressure drops to manageable levels. Even with successful atmospheric removal, Venus would remain hostile. Surface temperatures of 464 degrees Celsius would decrease only gradually, even with reduced solar input, because heat escapes slowly from the deep interior. The atmosphere would still contain sulfuric acid clouds until all sulfur compounds are removed, requiring chemical processing or biological scrubbing. The lack of water presents an enormous obstacle. Terraforming typically assumes introducing water to create oceans, but Venus would need an Earth ocean worth of water, roughly 1.4 billion cubic kilometers, transporting from somewhere. Comets could provide water, but directing enough comets to Venus to supply an ocean would require technology far beyond current capabilities and would take thousands of years, even with advanced propulsion. The absence of a magnetic field means even a successfully terraformed Venus would gradually lose any newly introduced atmosphere and water to solar wind stripping. Unless Venus's rotation could be accelerated to spin fast enough for dynamo action, or artificial magnetic field generators could be placed in orbit to shield the atmosphere, the terraformed planet would slowly revert toward its current state over millions of years. Some proposals suggest bombarding Venus with asteroids or comets from specific angles to transfer angular momentum and spin the planet faster, but the energies required are enormous, and the collateral destruction from such impacts might undo any terraforming progress. Realistically, terraforming Venus lies beyond foreseeable technology for centuries at minimum and possibly forever. The planet's current state is too extreme, the energy and material requirements for transformation too vast, and the maintenance requirements for preventing reversion too demanding. Venus serves better as a cautionary tale about planetary climate and a laboratory for understanding extreme environments than as a candidate for transformation into a second Earth. Any civilization capable of terraforming Venus could more easily build artificial habitats in space or terraform less hostile worlds like Mars. The far future of Venus is thus one of continued evolution under natural processes. The planet will slowly lose atmosphere over the next few billion years while the sun brightens and intensifies. Eventually, as the sun dies, Venus will either be destroyed entirely or transformed into a lifeless molten rock that later freezes into a barren sphere orbiting a white dwarf. There is no reprieve, no mechanism by which Venus could become habitable naturally. The planet is locked into its current hellish state for the remainder of its existence, however long that proves to be. Venus's story, from formation through potential early habitability to runaway greenhouse to eventual destruction, spans the entire history of the solar system from birth to death. Understanding this story provides perspective on planetary evolution and the ultimate fate of worlds, including our own. Chapter 15. Lessons from Earth's Evil Twin. Venus and Earth started as twins, 4.6 billion years ago, both formed in the same protoplanetary disk from the same mix of rock, metal, and volatiles. Both accreted mass through countless collisions during the chaotic early solar system. Both underwent differentiation, separating into iron cores, rocky mantles, and thin crusts. Both likely experienced massive impacts that melted their surfaces and created global magma oceans. Both possibly had water on their surfaces in their first billion years. Yet today, one world teems with life, while the other is a lifeless inferno. Understanding why these twins diverged so dramatically is one of the most important questions in planetary science, because the answer determines how common habitable worlds are in the universe and what factors allow planets to maintain habitable conditions for billions of years. Venus serves as Earth's evil twin, showing what can go wrong when planetary conditions cross critical thresholds and demonstrating that size and composition alone do not guarantee habitability. The greenhouse effect operates on both Venus and Earth, but with vastly different intensities. On Earth, greenhouse gases including water vapor, carbon dioxide, methane, and nitrous oxide absorb infrared radiation that the surface emits towards space. The gases re-emit this radiation in all directions, with about half directed back toward the surface. This trapped energy warms the planet. Without the greenhouse effect, Earth's average temperature would be approximately -18 degrees Celsius, cold enough to freeze the ocean solid. The natural greenhouse effect raises the average temperature to +15 degrees Celsius, creating the temperate climate that allowed life to flourish. Earth's greenhouse effect is self-regulating through negative feedbacks. The carbonate-silicate cycle removes carbon dioxide from the atmosphere over hundreds of thousands of years. When temperatures rise, weathering accelerates, removing more carbon dioxide and cooling the planet. When temperatures fall, weathering slows, allowing volcanic outgassing to rebuild atmospheric carbon dioxide and warm the planet. This thermostat has kept Earth's climate relatively stable for over 3 billion years. Venus experienced runaway greenhouse warming, where positive feedbacks overwhelmed any negative feedbacks. As solar luminosity increased, or as volcanic outgassing raised carbon dioxide levels, surface temperatures climbed. Higher temperatures evaporated more water from oceans. Water vapor is an extremely effective greenhouse gas, absorbing infrared radiation across broad wavelength ranges. More water vapor meant more warming, which caused more evaporation, creating an accelerating feedback loop. Eventually, the atmosphere became so opaque to infrared radiation that outgoing energy could not balance incoming solar energy regardless of temperature. Temperatures soared until all surface water evaporated. The steam atmosphere eventually photodissociated in the upper atmosphere, with hydrogen escaping to space and oxygen reacting with surface rocks. Carbon dioxide released by volcanism accumulated with nothing to remove it, because without water, the carbonate-silicate cycle could not function. The result was Venus's current atmosphere, 92 bars of carbon dioxide, creating surface temperatures of 737 Kelvin. The question planetary scientists grapple with is why Earth avoided Venus's fate. Several factors appear crucial. First, Earth orbits at 150 million kilometers from the Sun, while Venus orbits at 108 million kilometers. This 42 million kilometer difference means Venus receives about twice the solar energy per unit area that Earth does. The extra energy made Venus more susceptible to runaway warming because evaporation rates are higher and more energy is available to maintain a steam atmosphere. However, distance alone does not fully explain the divergence. Early in solar system history, the Sun was dimmer, and Venus may have received solar energy comparable to or only slightly higher than Earth receives today. If Venus had water and potentially habitable conditions early on, as some evidence suggests, then proximity to the Sun was not immediately fatal. Something else tipped Venus over the edge. The loss of water may have been the critical turning point. Once Venus lost its water through the runaway greenhouse and subsequent hydrogen escape, the the planet lost any chance of recovering. Water is essential for the carbonate-silicate cycle that regulates atmospheric carbon dioxide on Earth. Rain containing dissolved carbon dioxide forms carbonic acid that weathers rocks on land. Rivers carry dissolved minerals to the oceans, where organisms incorporate them into calcium carbonate shells and skeletons. These materials settle to the ocean floor and eventually get subducted through plate tectonics, carrying carbon into the mantle. Volcanic eruptions at subduction zones and hotspots release the carbon back to the atmosphere as carbon dioxide. This cycle operates over millions of years and prevents carbon dioxide from building up indefinitely or being removed completely. Without water, Venus had no weathering, no carbonate formation, no subduction of carbonates, and no regulation of atmospheric carbon dioxide. Every molecule of carbon dioxide, outgassed by volcanoes, remained in the atmosphere permanently, building toward the 92 bar pressure Venus has today. Plate tectonics is another factor that may explain Earth's success and Venus's failure. Earth has active plate tectonics driven by mantle convection. New oceanic crust forms at mid-ocean ridges, spreads across ocean basins, and subducts at convergent boundaries. This process recycles materials between surface and interior, regulates atmospheric composition through the carbonate-silicate cycle, and provides efficient heat loss from the interior. Venus lacks plate tectonics. The planet operates in a stagnant lid regime where a rigid lithosphere prevents convection from breaking through to the surface. Heat escapes less efficiently, possibly building up until episodic catastrophic resurfacing events release accumulated heat through widespread volcanism. The absence of plate tectonics on Venus may result from the loss of water. Water weakens rocks, lowers melting points, and lubricates faults. A dry Venus has a strong, rigid crust, resistant to the forces that initiate and maintain plate motion on Earth. The lack of a magnetic field may have accelerated Venus's atmospheric and water loss. Earth's magnetic field, generated by convection in the liquid outer core, creates a protective magnetosphere that shields the atmosphere from direct solar wind bombardment. Venus has no global magnetic field. The solar wind directly impacts Venus's upper atmosphere, stripping ions and accelerating atmospheric loss. Over billions of years, this enhanced loss contributed to removing hydrogen from the water that photodissociated in Venus's atmosphere. Earth's magnetic field also protected water vapor from being lost before it could condense and form oceans, potentially preventing Earth from experiencing the same runaway loss that Venus suffered. Why Venus lacks a magnetic field while Earth has one remains debated. The leading explanation involves rotation rate. Earth rotates once every 24 hours, fast enough that Coriolis forces organize core convection into patterns that generate magnetic fields through dynamo action. Venus rotates once every 243 days, possibly too slowly for effective dynamo action even if the core is liquid and convecting. These factors compound and interact. Venus's closer orbit provided more solar energy. Higher energy evaporated more water, initiating runaway greenhouse warming. The lack of a magnetic field allowed enhanced atmospheric loss of hydrogen from photodissociated water. The complete loss of water shut down the carbonate-silicate cycle and possibly stopped plate tectonics. Without plate tectonics and water, carbon dioxide accumulated indefinitely. The thick carbon dioxide atmosphere maintained extreme temperatures that prevented any recovery. Each factor reinforced the others, locking Venus into its current state with no way back. Earth avoided this fate through a combination of fortunate circumstances. Orbiting farther from the Sun provided a buffer against runaway warming. Maintaining water allowed the carbonate-silicate cycle to operate. Developing plate tectonics provided efficient carbon regulation and heat loss. Generating a magnetic field protected the atmosphere and water from solar wind stripping. The relevance to Earth's current climate challenges is direct and sobering. Human activities since the Industrial Revolution have increased atmospheric carbon dioxide from about 280 parts per million to over 420 parts per million as of 2025, the fastest rate of increase in millions of years. This increase drives global warming through enhanced greenhouse effect. While Earth is not on a path to becoming Venus in any foreseeable timeframe, the physics underlying both planets' climates is the same. Positive feedbacks that amplify warming exist on Earth. Melting ice reduces albedo, causing more solar absorption and more warming. Warming oceans release dissolved carbon dioxide, increasing atmospheric carbon dioxide and causing more warming. Thawing permafrost releases methane and carbon dioxide that were frozen for thousands of years, adding greenhouse gases and causing more warming. These feedbacks are not strong enough to cause a runaway effect on Earth at current or projected carbon dioxide levels, but they demonstrate that Earth's climate, like Venus's, responds to forcings through both amplifying and dampening mechanisms. Understanding Venus helps constrain climate models and identify the limits of Earth's climate system. Venus represents an end state, the result of greenhouse warming taken to completion without regulation. By studying how Venus's atmosphere operates, how energy is transporting, how clouds form and affect climate, and how greenhouse gases behave under extreme conditions, scientists gain insights applicable to understanding Earth's atmosphere. Computer models developed to simulate Venus's climate can be tested against observations and then applied to understanding extreme warming scenarios on Earth. Venus provides a laboratory for studying atmospheric physics under conditions Earth will never naturally experience, and the lessons learned inform predictions about Earth's climate response to continued carbon dioxide increases. The search for life beyond Earth benefits enormously from understanding Venus. Astronomers have discovered thousands of exoplanets, many of them rocky worlds orbiting in or near their stars' habitable zones. The habitable zone is the range of orbital distances where liquid water can exist on a planet's surface given reasonable assumptions about atmospheric composition and pressure. However, Venus orbits near the inner edge of our solar system's habitable zone, and it is utterly uninhabitable. This demonstrates that habitable zone boundaries are not hard limits guaranteeing habitability, but rather rough guides. A planet's actual habitability depends on many factors beyond orbital distance, including atmospheric composition, surface water inventory, volcanic activity, magnetic field strength, rotation rate, and evolutionary history. Identifying truly habitable exoplanets requires distinguishing between Earth-like and Venus-like worlds. This is extremely challenging because current technology can only detect a few basic properties of exoplanets such as mass, radius, orbital period, and in rare cases, some atmospheric composition information. Determining whether a given rocky exoplanet in the habitable zone resembles Earth or Venus requires detailed atmospheric characterization. Recent research suggests that detecting sulfur dioxide in an exoplanet atmosphere might indicate a Venus-like world because sulfur dioxide is abundant on Venus, but rapidly removed from Earth's atmosphere by rain. Detecting oxygen or ozone might indicate an Earth-like world with photosynthetic life producing oxygen. However, interpreting these signatures requires understanding how atmospheres on rocky planets evolve and what processes besides life can produce biosignature gases. Venus provides a nearby example of an alternative evolutionary pathway that rocky planets can follow, cautioning against assuming that all Earth-sized planets in habitable zones are habitable. Comparative planetology, studying multiple planets to understand the factors controlling planetary evolution, fundamentally depends on Venus. With only Earth as an example, scientists could not determine which of Earth's properties are essential for habitability and which are incidental. Venus, being so similar to Earth in size and composition, yet so different in outcome, provides crucial constraints. Mars adds another data point, showing the consequences of being smaller and forming with less water. Together, Venus, Earth, and Mars span a range of outcomes for terrestrial planets and illustrate how sensitive planetary evolution is to initial conditions and orbital parameters. The study of these three worlds forms the foundation for understanding rocky planet evolution throughout the galaxy. The divergence of Venus and Earth also raises profound philosophical questions about contingency and determinism in planetary evolution. Were Venus and Earth destined from formation to follow their respective paths, or could small changes in initial conditions have swapped their fates? If Venus had formed a few million kilometers farther from the Sun, would it be habitable today? If Earth had formed slightly closer, would it have become a hellish world? If Venus had been struck by a different set of impacts during formation, might it have retained more water or developed a faster rotation and magnetic field? These questions likely have no definitive answers because we cannot rerun planetary formation and observe alternative outcomes. However, contemplating them emphasizes that habitability may be a delicate balance easily tipped by factors that seem minor but have profound long-term consequences. Venus stands as a monument to planetary evolution gone wrong, a cautionary tale written in sulfuric acid and carbon dioxide. The planet demonstrates that worlds similar to Earth in size and composition can nevertheless become utterly hostile through processes operating over billions of years. Venus teaches us that atmospheres are not static, but evolve in response to solar forcing, volcanic activity, and surface-atmosphere interactions. Venus shows us that water is precious, essential not just for life, but for regulating planetary climates through mechanisms like the carbonate-silicate cycle. Venus warns us that positive feedbacks can dominate planetary climates once critical thresholds are crossed, leading to irreversible changes. Every measurement of Venus, every spacecraft that braves its atmosphere and surface, every model that simulates its climate, adds to our understanding not just of that distant world, but of our own. Venus is Earth's evil twin, and understanding the twin illuminates the original. Chapter 16. Conclusion: Venus's place in the cosmos. The story of Venus is ultimately a story about possibility and fate. It is the story of a world that may have begun with promise, a planet that could have developed seas and continents, stable climates, and perhaps even life. It is the story of how that potential was lost, how a planet remarkably similar to Earth in fundamental properties diverged catastrophically toward an outcome so hostile that nothing resembling life, as we understand it, could survive there. Venus represents a road not taken by Earth, an alternative evolutionary pathway that rocky planets can follow. The planet stands as evidence that the universe contains vast diversity of worlds, that planets with similar origins can reach radically different destinations, and that the factors determining whether a world remains habitable or becomes hellish are subtle and interconnected. From Venus's formation 4.6 billion years ago in the swirling disk of gas and dust surrounding the infant sun, through its violent youth of giant impacts and magma oceans, through its possible era of oceans and moderate temperatures, through the catastrophic runaway greenhouse that boiled away its water and transformed its atmosphere into a crushing toxic envelope, through episodic resurfacing that erased most evidence of its ancient past. Through billions of years of slowly evolving toward its current extreme state, Venus has journeyed through time as a planet shaped by physics and chemistry operating under conditions unique in our solar system. Every stage of this journey teaches us something about planetary science. The Soviet Venera program proved that humans could build machines capable of surviving and functioning in the most hostile environment any spacecraft has ever encountered. 8 landers successfully touched down on Venus's surface between 1970 and 1982, transmitting data and images that revealed a rocky volcanic landscape heated to temperatures that melt lead, crushed by atmospheric pressure equivalent to being a kilometer underwater. Those missions required engineering ingenuity and persistence through repeated failures. They demonstrated that exploration of extreme environments is possible when driven by determination and willingness to learn from setbacks. The fact that no spacecraft has landed on Venus in over 40 years, despite tremendous advances in technology, highlights just how challenging Venus exploration remains. American missions took a different approach, studying Venus from orbit and through atmospheric probes. Pioneer Venus operated for 14 years, far exceeding its design lifetime, mapping Venus's surface with radar, studying its atmosphere in detail, measuring the solar-wind interaction, and establishing that Venus has no magnetic field. Magellan produced radar maps of 98% of Venus's surface at resolutions revealing geological features in unprecedented detail. Those maps remain the foundation of Venus geology 3 decades after the mission ended. The maps showed a world dominated by volcanism, with shield volcanoes, vast lava plains, coronae, pancake domes, tesserae highlands, and evidence of a global resurfacing event within the last billion years. Venus Express and Akatsuki brought Venus back into focus in the 21st century after years of relative neglect. Venus Express discovered the dynamic polar vortex, monitored atmospheric composition variations, possibly indicating volcanic activity, confirmed lightning, detected ozone in the upper atmosphere, and measured how Venus's rotation rate varies over time. Akatsuki detected massive stationary gravity waves, discovered an equatorial jet in the lower atmosphere, created three-dimensional meteorological maps, and tracked cloud patterns revealing Venus's complex weather. These missions proved that Venus is not a static world, but a planet with active atmospheric circulation, possible ongoing geological activity, and mysteries that continue challenging our understanding. The phosphine controversy, beginning in 2020, reinvigorated Venus science by raising the possibility of life in the clouds. Whether phosphine truly exists in Venus's atmosphere remains debated. Whether Venusian clouds could harbor microbial life remains speculative. But the questions forced the scientific community to seriously consider Venus as an astrobiological target, to examine what conditions might allow life to exist in such hostile environments, and to plan future missions capable of detecting biosignatures if they exist. Venus joined Mars and the icy moons as a world where the search for life might yield results, a remarkable development for a planet long dismissed as sterile. The upcoming missions in the late 2020s and 2030s promise a new golden age of Venus exploration. DAVINCI will descend through the atmosphere, measuring composition with unprecedented precision and photographing the surface during its fall. VERITAS will map topography and geology at resolutions 10 times better than Magellan. Envision will probe beneath the surface with ground-penetrating radar while mapping composition and monitoring for volcanic activity. India's Chakrayan will add atmospheric and surface studies from its elliptical orbit. Private missions like Rocket Lab's Venus Life Finder will demonstrate that commercial spaceflight can contribute to planetary science. Together, this fleet will transform our knowledge of Venus, answering questions that have persisted for decades and raising new questions that will drive the next generation of exploration. Venus's far future is sealed by stellar evolution. Over billions of years, the planet will continue losing atmosphere to space while the brightening sun increases surface energy input. Eventually, 6 to 7 billion years from now, the sun will swell into a red giant, possibly engulfing Venus and destroying it completely, or at minimum stripping away its atmosphere and melting the surface into a global magma ocean. After the sun sheds its outer layers and becomes a white dwarf, Venus, if it survives, will slowly freeze into a dark, airless rock orbiting a dying star. This far future awaits all planets in the inner solar system. Earth will suffer the same fate as Venus, perhaps slightly later, depending on the exact evolution of the sun's size during the red giant phase. All terrestrial worlds are temporary, their habitability windows limited to the main sequence lifetimes of their stars. The lessons Venus teaches about climate, habitability, and planetary evolution extend far beyond one planet. Venus demonstrates that greenhouse effects can run away if conditions exceed critical thresholds. Venus shows that water is essential for climate regulation through mechanisms like the carbonate-silicate cycle. Venus illustrates that plate tectonics and magnetic fields play crucial roles in maintaining habitable conditions over billions of years. Venus proves that habitable zone boundaries are fuzzy, that planets near those boundaries can be hostile despite receiving appropriate amounts of stellar energy. Venus warns that planetary climates respond to forcings through complex feedbacks that can amplify small changes into large effects. For Earth, Venus serves as a reminder of what we could lose. Our planet's habitability is not guaranteed permanently. While Earth will not become Venus due to human-caused climate change, the physics underlying both planets' climates is fundamentally the same. Understanding how greenhouse effects work, how feedbacks amplify or dampen changes, how atmospheres respond to increased carbon dioxide, and how planetary systems can cross tipping points beyond which recovery becomes impossible informs how we think about Earth's climate and the consequences of our actions. Venus exists as a natural experiment in extreme climate, a laboratory showing the final result of greenhouse warming without regulation. For astrobiology and the search for life in the universe, Venus provides crucial context. Of the countless exoplanets discovered, many are Venus-like rather than Earth-like. Hot super-Earths orbiting close to their stars, tidally locked worlds with permanent day and night sides, planets with thick atmospheres and high surface pressures are all variations on themes Venus exemplifies. Understanding Venus helps us interpret observations of distant worlds and predict which exoplanets might harbor life and which are sterile. The diversity of outcomes for terrestrial planets in our own solar system, with Venus, Earth, and Mars all following different paths, suggests that exoplanets show even greater diversity. Finding habitable worlds requires not just identifying planets in habitable zones, but distinguishing the rare Earth-like worlds from the more common Venus-like or Mars-like alternatives. Venus reminds us of the preciousness of Earth. In all the solar system, only one world developed conditions allowing complex life to flourish. Only one planet maintained liquid water oceans for billions of years. Only one world found the balance of factors that allowed carbon-based life to originate, evolve, and diversify into the incredible biosphere we see today. Earth succeeded where Venus failed, and Mars never achieved what Earth accomplished. This makes Earth extraordinary, not because of size or position alone, but because of the combination of factors that align to create and maintain habitability. We live on the one world among 3 terrestrial planets that remains welcoming to life, and we should not take that for granted. The complete story of Venus spans from the planet's birth in fire and chaos, through its possible golden age if it ever had one, through its transformation into hell, through humanity's first halting steps to explore it, through decades of observations and discoveries, to the upcoming missions that will probe deeper into its mysteries than ever before. The story is not finished. Every mission adds new chapters. Every discovery raises new questions. Venus will continue surprising us, challenging our theories, and teaching us about how planets work. The planet that once seemed too hostile to bother studying has become one of the most important worlds for understanding planetary science, astrobiology, and the diversity of outcomes that terrestrial planets can experience. Right now, as you finish reading this, Venus hangs in Earth's sky, shining brighter than any star. The ancient Romans called it the evening star and the morning star, never knowing they were seeing the same world. They named it for the goddess of love and beauty, attracted by its brilliance and grace in the twilight sky. They had no idea that the beautiful light concealed a nightmare world of sulfuric acid clouds, crushing pressures, and temperatures hot enough to melt lead. They could not have imagined that this sister world to Earth had become what we now call Earth's evil twin. But they looked up at Venus and wondered, as humans have always wondered about the lights in the sky. We now know what Venus is. We have sent machines to touch its surface, to photograph its rocks, to breathe its atmosphere and measure its properties. We have mapped nearly its entire surface with radar, seeing through the clouds to the volcanic plains and ancient highlands beneath. We have discovered its mysteries, including the slow backward rotation, the superrotating atmosphere, the missing magnetic field, the possible hints of life in the clouds. We understand in broad strokes why Venus became what it is and why Earth did not. But the details remain elusive, and the most fundamental questions about Venus's history await answers from future missions. Venus represents humanity's drive to explore the unknown, to venture into hostile places, to seek knowledge even when conditions are unforgiving. The planet has destroyed every spacecraft that landed on it through heat and pressure, yet we keep returning because the secrets Venus holds are too valuable to ignore. Understanding Venus helps us understand our own planet, our place in the solar system, and the chances that life exists elsewhere in the universe. Every mission to Venus is an investment in knowledge that pays dividends far beyond the immediate discoveries. If you found this story of Venus compelling, if the tale of Earth's evil twin captured your imagination, if the science and exploration excited your curiosity, then show your support. Hit that like button. It tells us that you value deep explorations of planetary science and want more content diving into the stories of worlds beyond Earth. Subscribe to this channel so you never miss when we explore other cosmic mysteries, whether it is the frozen moons of the outer solar system, the extreme physics of neutron stars, or the search for habitable worlds around distant suns. Turn on notifications so you are alerted immediately when new content appears. Share this video with anyone who loves space, science, or simply great stories about how the universe works. Leave a comment sharing what aspect of Venus's story fascinated you most, or what world you want us to explore next. The universe is vast, filled with billions of worlds, each with its own story written in rock and ice and fire. Venus is just one planet, one story among countless others, but it is our nearest planetary neighbor, a world we can study in detail, a place that teaches us profound lessons about planets and climates and the factors that make worlds habitable or hostile. Venus matters, its story matters, and your engagement helps us continue telling these stories to a wider audience. Thank you for joining us on this journey through the complete story of Venus, from birth to potential death, from discovery to future exploration. The morning star shines above us, beautiful and deadly, a world of wonders and terrors. We have only begun to unravel its secrets. The best chapters of Venus exploration lie ahead, and we will be here to share those discoveries with you as humanity returns to Earth's evil twin.